Shall we get started? I think it's almost time. Let me adjust the microphone here. Okay, is this better? Yeah. There's no echo, that's the good part. Okay, so today we're going to continue memory latency, which we started last time, which, as we discussed, is a critical topic that affects everything else that we do in our systems. If your latencies are high, you basically design your system to tolerate those latencies, and your system becomes a lot more complex. If your latencies are high, also you need to increase the bandwidth in your system so that you can actually try to tolerate those latencies. And again, your system becomes more complex. So this is a root cause that complicates our systems. Yet this is another example where maybe mindset issues are getting in the way of fixing the problem. Is there a lot of light over here? Is it okay? I feel like there's a lot of light. What should we do? Projection, room, light. Is this better? What do you think? Now you guys have more light. You don't sleep, but maybe you can focus better. Is that okay? Okay, let's do this one. Okay, so we'll continue the exploration of memory latency. Let's see if we can get to memory controllers. This is 9A, but we have a lot of ideas. Basically, we're going to cover a lot of ideas. We had started covering some ideas in the last lecture. And please ask questions like last time. Let's keep it interactive. Remember, these are some slides to get your cache warmed up. We discussed that there are two major sources of latency and efficiency. Modern memory in general. We're looking at DRAM, but this is true for many memories in general. They're not designed for low latency. Main focus is really cost per bit, capacity, except for SRAMs on chip, maybe. But even then, the big portion of them are designed for capacity also. And modern DRAM latency, memory latency in general, is determined by worst case condition and worst case devices. And our goal was to look at the latency problem in a fundamental way and try to reduce it at the source of the problem. And we were looking at basically the major reasons for latency, high latency. One is due to design, and the second is due to how we approach specifying the latencies. We'll continue to talk about the first one. How can we change the design of the memory microarchitecture so that we can actually make latency, let's say, a first-class citizen, so that we can optimize for it, as opposed to mainly optimizing for cost, which is capacity per area. And then we're going to switch to the second reason over here, which may be even easier to adopt, as we will see today. Does that sound good? Okay, cool. So we discussed this idea of tiered latency DRAM, which is a heterogeneous architecture that introduces heterogeneity into the subarrays by using isolation transistors, where a small portion of the subarray can be used as a low latency memory, and you can use that as a cache for the high latency portion of the memory. I'm not going to go over that, but we discussed this last time. If you have any questions, feel free to ask. Let's talk about some other ideas. I'm going to give you some examples of how you can reduce latency if you think out of the box, let's say. Remember, we discussed the idea of row clone, right? Cloning the rows. Tiered latency DRAM actually takes advantage of row clone that copies rows between different rows in the same subarray very fast. So we're going to try to extend that across subarrays over here. And I'm going to use the same motivation, but this is going to actually have some other benefits in terms of reducing latency. We were discussing bulk data movement in applications in earlier lectures. I believe it was lecture 4 or so. And we discussed that bulk data movement happens a lot in real applications. This is a beautiful paper by Google that talks about some of that. And you can see that if you want to move a row, a 4 kilobyte page to another 4 kilobyte page, basically you have to go through the memory channel back and forth, right? Do the copy, which is very inefficient, as we have discussed earlier. Now, this is long latency. This is also high energy, basically. I think latency and energy are actually coupled in some way. If you keep increasing latency, that means that you're actually exercising interconnects more and more. And interconnects don't come for free. They're actually expensive in terms of energy. So reducing latency fundamentally usually reduces energy as well. This is actually, basically, you get two benefits at one time by reducing latency. So keep this in mind. Remember, our goal was to always improve performance as well as reduce energy. So reducing latency will help that, actually. So I think this is actually good to think about, because if we keep the current paradigm where we keep increasing the latencies, then energy is also going to increase. So basically moving data inside DRAM. So if you have a bank over here and you have different subarrays, row clone, if you want to copy a source page to a destination page, if they're inside the same subarray, that's easy. We said that 2 consecutive activates can enable that very efficiently, right? We said 90 nanoseconds in the row clone paper. You may be reading row clone paper in your homework, for example, and reviewing it. By the way, in your homework, we give you a lot of freedom. You have lots of papers that you can review. This is all potential extra credit for you. So this course actually is, in my opinion, very easy, because you can do a lot of extra credit assignments, and you can actually get a relatively easy 6 in this course, I would say. And many people actually have done that because the extra credit gives you a lot of freedom in terms of like what flexibility in terms of focusing your efforts on, for example, reviewing papers or doing extra credit labs or doing something else extra credit. There'll be extra credit in the exam also. So basically, even though there might look like there's a lot of material, a lot of it is really extra credit in the sense that you can actually get 120 points in the course as opposed to 100 points, right? Or if you were getting 80 points, if you have done some extra credit, you can get 100 points. Yeah. So keep that in mind when you're approaching the homeworks. For example, you can read the row clone paper as an extra credit paper and review it. And we've discussed it a lot, actually. So it'll be an easy extra credit, in my opinion. Okay, so going back, row clone enables copy of one row to another row inside one subarray relatively quickly. But what do you do across subarrays? Unfortunately, across subarrays, you're stuck because you don't have any connections between the subarrays. You have to go through the internal data bus. And that actually causes a lot of problems. And in the row clone work, we discussed that you have to actually copy the data from one subarray to another bank first through this internal data bus, which takes a lot of time. And then you have to copy the data back from that temporary row in some other bank to subarray 2, for example, if that's where your destination row resides. Again, using this internal data bus, which is narrow. The good thing is this is still good for energy because you're not going off chip. You're copying data within the DRAM chip from one subarray to another subarray by using a temporary row in some other bank. But this is not the best you can do, basically. The problem is really you have low connectivity between these subarrays. And by solving that, you can actually make the data movement much better. I like this idea because this is actually very interesting. The way we design our memories, we try to minimize the connectivity to reduce cost. But if you think about improving performance, latency, and even sometimes energy, you actually want to have higher connectivity. I like thinking about the analogy with the brain also over here, right? Our brains actually have a lot of connectivity inside them. The way we're designing our memories don't have a lot of connectivity. So I like this idea because it's going to increase the connectivity inside the DRAM chip. That's the idea, basically. Provide a new substrate to enable wide connectivity between subarrays. And how do you do that? Essentially, we want to support fast bulk data movement between subarrays. That was the original goal, but you will see that this actually has some additional benefits in terms of latency. How do you do that? Basically, add some isolation transistors between the subarrays. Let's take a look at them. Subarrays normally are not connected to each other. They basically have no connection between them. We're going to add these isolation transistors that we introduced in tiered latency DRAM within a subarray. But now we're going to add them between subarrays. So if you enable these transistors, this subarray will be connected to this subarray. So the bit lines will be connected. That's the beauty. If you disable them, it's like existing DRAM architecture. And this will enable you a wide data path to copy one row from one subarray to another subarray. That's the basic idea. It's very simple, as we will see also. And this actually enables multiple applications. You can see that there's fast bulk data copy. Copy latency between subarrays reduces significantly by almost, let's say, 9x, actually 9.2x. Energy also improves. It is not said here, but it's kind of the application level result is given. You can actually enable in-DRAM caching. We will see that by using heterogeneous subarrays, some large subarrays and some small subarrays, or slow versus fast subarrays. And you can also improve the pre-charge latency, as we will see, because once the subarrays are connected to each other, they can use each other as pre-charge units. Okay, so let's take a look at how this is done. So basically, you have subarray 1 over here. These are the sense amplifiers and the pre-charge circuitry. That's what S and P stand for. And we add these isolation transistors between the subarrays. And we introduce a new command called row buffer movement. So let's say you activate subarray 1. This is normal activation, one row in subarray 1. It gets stored in the sense amplifiers and amplified. Now, this is what the bit lines look like in the subarray 1. Basically, they're all VDD, assuming all values are 1 over here. That's what I'm assuming over here for simplicity purposes. Here, it's precharged. The second subarray is precharged, right? Now, if I activate these isolation transistors, meaning that I want to move the row that's activated in subarray 1 to the bit lines in subarray 2, this is what you do. You send a command called row buffer movement, subarray 1 to subarray 2. These isolation transistors get connected to the sense amplifiers, which means that the sense amplifiers share the charge with the isolation transistors, with the bit lines in subarray 2. And they basically perturb the bit lines. And because of charge sharing, what happens is the sense amplifiers down in the subarray get activated and they amplify the charge. So they store the value that was stored in the sense amplifiers over here. That's how you can move one row buffer, which is here, to another row buffer that's here. Does that make sense? Basically, it's very simple. It's again based on charge sharing principles. And eventually you restore the charge in all of the cells. So it's beautiful. Now you've enabled a longer bit line essentially, right? Before we were using the isolation transistors to enable shorter bit lines. You can think of this as using isolation transistors. By enabling the isolation transistors, you're enabling a longer bit line so that you can transfer one row that's here to another row that's here using the sense amplification circuitry. Okay, basically you transfer an entire row between two subarrays this way. You could imagine extending this, right? There could be another subarray over here, and then you connect the sense amplifiers over here. That way you enable an even longer bit line, so you could actually span a distance of two subarrays that way. But of course, if you keep extending it, the latency on the bit line becomes longer and longer, and maybe the movement is actually slower and slower. Maybe at some point it doesn't make sense to do this. Okay, so in the paper, if you choose to read it, you can actually see that we actually propose doing this at most between 3 subarrays like this. If you want to move data from subarray 1 to subarray 3, you do this. Now, if you want to move the data from subarray 3 to subarray 5, again, you do this between subarray 3, 4, 5. So you can actually keep moving the data this way, right? So it doesn't matter how many subarrays you have, but except it's a serial data movement. It's still better than using the internal data bus in general. And the paper has some analysis on this if you're interested. And there's a lot of evaluation in the paper that I'm not going to go into here. But this way, you can actually get a lot higher bandwidth than an external memory channel. In the paper, there's some analysis, assuming some conservative guard bands, because you need to assume some guard bands, right? Because there may be some latency problems, as we will, there may be some reliability problems, as we will see. But you can move 4 kilobyte data in 8 nanoseconds, according to the calculations in this paper, which is actually much higher than the bandwidth of a single reasonably fast DDR4 channel at the time. This was published in 2016. So you can actually do the calculations today and you'll get even higher numbers. And the area overhead is relatively small, and you can read the paper. So the area overhead essentially is these transistors, right? Again. Okay. So let's see what kind of use cases this can enable. This can enable clearly copying data between subarrays. As I mentioned, you activate the source row in subarray 1, which brings data into sense amplifiers. You do the row buffer movement, which enables the isolation transistors and moves the data or copies the data from the sense amplifiers over here to the sense amplifiers over here. And then once you activate the destination row over here, you move the data from the sense amplifiers here to the destination row. It's very similar to row clone, except there's another step between the two activates, which is the row buffer movement command. And as I said, this reduces a 4 kilobyte row copy latency by 9.2x and energy consumed for 4 kilobyte row copy by 48x. So this actually gets closer to doing row clone inside the same subarray. It's not exactly the same, but it's close enough. Of course, if you're doing it across 2 subarrays over here. If you go to 3 or 4, then it becomes different. So this enables other things, as I mentioned. I'll quickly mention them. So remember, we were looking at long bit lines. Long bit lines are not great because the latency is high. So you can actually reduce the latency by making your subarray smaller. So think of this as a subarray. I show a picture of 4 word lines over here, but you can think of it as 512,024 rows. Now you can chop it into shorter bit lines, smaller subarrays. This is clearly lower latency. Faster activate and pre-charge time, basically, because of the shorter bit lines. But unfortunately, having smaller subarrays lead to high area overhead. So you don't want to have smaller subarrays everywhere. But maybe there is a sweet spot where you can have a heterogeneous design. You have a lot of slow subarrays, but interleaved with some fast subarrays. And the goal of the fast subarrays is clearly fast access latency. And in the fast subarrays, you cache data that you deem to be hot. So that's another way of designing heterogeneous latency architecture. We showed tiered latency DRAM. What it was doing was it was taking a single subarray, dividing it into two portions, fast and slow, by isolating them using isolation transistors. Here you can also do that in the slow subarray, but separately from that, you actually add some fast subarrays that are fundamentally faster. These are 32 rows in the subarray, basically. Bit lines are fundamentally shorter. Now, the beauty of this is you can figure out which data is accessed heavily, frequently in the slow subarray and move it to the fast subarray. And the memory controller uses the fast subarray as a cache. Right? Just like in tiered latency DRAM, we use the faster part, near segment as a cache. So caching algorithms may be similar. So the issue over here is it requires movement of data rows if you want to do this caching dynamically, which usually you want to do it dynamically. Yes, please. Maybe you can press the button over there so that people, that's the beauty of this room. Yes.
Well, with this configuration with the fast subarray, could we maybe then only integrate Mbit in the fast subarray? It is because this will be equivalent to have, like, when we have a processor, we basically have caches. So in this case, the cache is a fast subarray, and so the computation would be like done in the fast subarray.
Potentially, yes. Yeah, sure, potentially. That could be a design decision. If you're cost sensitive, for example, you may just decide to put Mbit only in the fast subarrays, right? But if you're not that cost sensitive, it doesn't hurt probably to do it everywhere. But yeah, it gives you some more options in terms of where you can potentially integrate. Good question. Okay, I'll move on. So basically, by using this LISA, low-cost interlinked subarray substrate, using the isolation transistors, you have a very fast caching mechanism, right? You can move data from slow subarray to fast subarray, and if you need to, back from fast subarray to slow subarray. Whereas this didn't exist before. If you did not have these isolation transistors, you have to go through something else. So caching the rows is very difficult. And basically, the work shows that you can reduce the hot data access latency significantly with relatively small overhead. And you can read the paper for more detail. But this opens a huge design space also, right? How many fast subarrays do you have? What fraction? Again, your cost sensitivity is important over here. Okay, let me give you another example of how this idea enables faster DRAM. And the goal, the history of this work is that we wanted to really solve the problem with row clone, which is inter-subarray data movement. So we clearly solved it. But it turns out solving that using this idea by increasing connectivity between subarrays enables other benefits like link precharge. And the problem is that the precharge time is limited by the strength of a precharge unit. So what does precharge mean? As we discussed, you need to set the bit lines from the values that they have in the active, when the row is activated, to VDD over 2. Right? Basically, you need to reset the bit lines, essentially. You can think of it that way. And that requires a strong precharge unit to change the voltages in all of the bit lines. And normally, the way it's done is you have one precharge unit over here that drives the bit lines and sets them to VDD over 2. And that's conventional DRAM. But now, if you're able to link another subarray to this subarray, you can use both precharge units. That's the idea. So this is showing that both precharge units normally in this subarray can also help the precharge units in this subarray. That way, you can actually do the precharge much faster because you were using two precharge units actually to set the bit lines. And it turns out this actually reduces the precharge latency a lot, as you can see, even with guard bands, meaning you add some guard band to make sure that there are no reliability issues, your latency reduction is quite significant, which affects the performance also. There are application level results that are in the paper that I mentioned earlier in an earlier slide, but you can read that if you're interested. And that's the paper. Any questions? Actually, I like this work a lot. I think we need to increase the connectivity within DRAM banks. There should be more work in this area. Mohammed had done some work on network on memory. I don't have slides on that, but you can take a look at that if you're interested. That basically uses 3D stacked memory and layers in 3D stacked memory to connect the banks to each other in a much faster way. Correct, Mohammed? And that reduces essentially the interbank copy latency, for example, of row clone. But I don't know of any other work that tries to increase the connectivity more. I think we need more of this in a simple way, of course. Yes. Please press the button. I'll remind you.
In the case of the 3D memory, if we do interconnect more the banks, then the message protocol wouldn't be needed anymore, right?
What is the message protocol? What do you mean by that?
We saw really briefly that basically to communicate with each other, the different banks in the 3D memory basically have message like
network on chip, let's say.
Exactly.
On chip network, yes.
Yeah.
I mean, you still need some sort of communication mechanism between the banks, right? Depending on how you design it. But that could be designed to be low cost. We're going to cover interconnects in the later part of this lecture. You will see that all of the design space of interconnects applies over there. So you could have a simple bus, but that's not a good idea in general. You could have a ring, for example, which is relatively low cost, or you could have dynamically switched routers on chip. That clearly increases the cost. Right? Yeah. So you need some sort of protocol in the end. Yeah. But the complexity of the interconnect and the protocol depends on how much cost you can pay. Yeah.
So fast subarray means a shorter bit line and a faster precharge or stronger precharge unit.
No, fast subarray means these are orthogonal ideas. Basically, fast subarray here is shorter bit line. That's it. This is an orthogonal idea that can be used in combination with fast subarray. Yeah. All three ideas are orthogonal, actually, but they're enabled by this substrate. Okay. So let me move on. As I said, I'm going to give you a lot of ideas in this lecture. I think a lot of them are good ideas. This is another idea that approaches things in a slightly different way. And you'll see that this is slightly different from tiered latency DRAM, even though it may look like it. So basically, actually, this work covers multiple things, like trying to fix DRAM scaling challenges, latency, refresh, and also RowHammer type of challenges. I'm not going to talk about the third one. Maybe I'll briefly mention it, but I don't have slides on it. But if you look at conventional DRAM, this is what a subarray looks like, right? And we've seen this before. You activate a row, and then you don't have any options, basically. So the idea in this work is have some set of rows as part of the subarray that are called copy rows that could be used for multiple purposes again. This is different from tiered latency DRAM because you can see that there are no isolation transistors over here. You have two different decoders. One is the regular decoder, one is the crow decoder. If you want to access the copy rows, you activate the copy row decoder. But these are two independent decoders, and we will see why that's useful for. So you can copy data from a regular row to a copy row. And we know how to do that, right? Using row clone. So that's not new. But what this work proposes is once you copy one row's data from here to a copy row, you can also do multiple row activation. Activate two rows concurrently. Now, what does this do? This basically connects two cells in a given bit line that have the same value to the same bit line, which means that the chart sharing is much faster that way, because now you're driving the bit line using two cells. And that actually reduces the latency of access. That's the idea. And you're doing that clear. For this to happen, of course, these two rows need to have the same values, right? So this is charged, this is charged, this is discharged, this is discharged. Basically, you need to have copied the row from here to here. That's the idea. So let's take a look at use cases. You can actually use this as a cache also again. It's a slightly different cache than the tiered latency DRAM. First, you copy the frequently accessed row, let's say, you copy it to the copy row. And then the next time you access that row, you do multiple row activation, and this reduces access latency for that row. And if you're accessing, if you're accessing frequently accessed rows always using copy rows, you actually get a lot of benefits. And then crow ref, this is another idea. Basically, you may find out that a row over here is a weak cell, so it needs to be refreshed relatively frequently. But some rows over here are quite strong. based on retention time profiling you can figure out. And it can remap a weak row to a strong row so that you never access this row. You always access this row instead. That's the idea. We remap a weak row to a strong row, essentially. And that reduces DRAM refresh overhead because strong row hopefully doesn't need to be refreshed as frequently. This is if you know the retention times of the cells, you can actually, this is another idea that you can enable basically. We have discussed the retention times in the past, as you remember. Yes?
What is weak and strong row?
No, here weak in terms of retention time. Weak means that it can lose its charge much faster. Yeah. And strong means that it doesn't lose its charge fast. So it can be, this has to be refreshed, let's say every 64 milliseconds, but this has to be refreshed every 250 milliseconds. That way you can actually reduce the refresh rate because you're never using the weak rows. Exactly, that's right. It has nothing to do with, you need to figure out what is weak and what is strong based on the profiling mechanisms that we discussed in an earlier lecture. Okay, so that's the basic idea. And then the paper proposed a mechanism for protecting against RowHammer. I will briefly mention the idea. Basically, for example, if you're hammering a row over here, you detect that somehow using access counters, block hammer, etc., and move the row to basically remap the row to a row over here so that it doesn't disturb those victim rows over there again. And then you can keep doing that dynamically. But the paper doesn't go into a lot of detail. But it's a basic idea that's proposed. Basically, you can actually swap the row or remap the row that you're hammering. Okay, so there are some results in the paper which are actually quite good. You can read the paper for more detail. Of course, this comes. So this is another idea that reduces both performance as well, that improves both performance as well as energy, as you can see. If you combine the caching mechanism with the refresh mechanism that we discussed, you improve performance as well as energy significantly. And the hardware overhead, clearly there's some hardware overhead, right? Because you're adding these copy rows. So where's the hardware overhead coming from? There's some storage overhead because copy rows are used just for copy. There's some hardware overhead because you have another decoder over here. So there's overhead, as you can see. So you lose some DRAM capacity. And there's some memory controller storage to keep track of which rows are remapped where, clearly. But you can read the paper and you can imagine things. And we're going to talk about simulation at some point. A lot of these simulations are done using Ramulator, which is a simulator that we have developed for more than a decade, longer than a decade. And we may talk about that at some point. Okay. Any questions? Okay. Let me give you another idea. So there are ideas actually. Once you start thinking creatively about reducing latency, what else can you do? And this is one of the state-of-the-art works. But the beauty of research is you can always come up with a better idea, right? Or new ideas. So I'd encourage people to think about new ideas. This is an interesting idea because it targets something a little bit different, basically. And essentially, workloads have different capacity and latency demands. If you look at the previous works that we have discussed, for example, tiered latency DRAM, it makes a static capacity latency trade-off at design time. You choose the near segment size statically, right? You choose, for example, in the heterogeneous subarrays, you choose the subarray sizes statically. In Crove, you choose the size of the copy rows, how many copy rows you have statically. All of these are fixed at design time, meaning somebody designs a chip and they don't change, right? It's not configurable in the sense. The goal here was to make things a little bit more configurable because sometimes maybe you want to use that area for capacity, right? If you're running out of capacity. Maybe you don't care about latency in some cases. I'm not going to argue that too much, but basically you need to have something configurable to get a good trade-off. And the goal of this work was to actually have a low-cost architecture that can be dynamically configured to have high capacity or low latency at a fine granularity. So basically, you can configure a DRAM row to have high storage capacity, or if you really need fast access to some data, you can configure a DRAM row to be low latency. And to be able to do that efficiently is the key question. And this paper provides a substrate to do that, essentially. You have your DRAM, essentially a row, a single DRAM row can switch between max capacity mode or high performance mode. And the key idea, again, is to configure connections in the bit lines, as we have been doing so far. And here we're going to configure the connections between the bit lines and the sense amplifiers. So I'll give you an example. Actually, this goes into a little bit more detail. The way modern DRAM is designed, it looks like this, basically. You have two sense amplifiers on different sides. I'm kind of introducing something. This is actually introduced in the Lisa paper, but I kind of overlooked it. But you have an open bit line architecture, meaning these cells over here are connected to the sense amplifier on top, and these cells over here are connected to the sense amplifier in the bottom. And the reason sense amplifiers are quite large, and you need to actually play a lot of tricks to put your sense amplifiers in the right place. So this open bit line architecture enables you to charge these cells in these sense amplifiers, this bit line in this sense amplifier, and this bit line in this sense amplifier. That's how it is today, basically. But there's no connection over here. So we're going to add connections over there. So what we're going to do is we're going to add isolation transistors again, so that these connections are configurable or reconfigurable. These are called bit line mode select transistors. If you read the paper, there's actually a little bit more that you need to add, but I'm not going to go into it. And this will enable us to switch between multiple different modes. Now let's take a look at those different modes. The max capacity mode, you basically mimic the current architecture, right? Current architecture looks like this, right? Basically, this bit line is connected to this sense amplifier, this bit line is connected to this sense amplifier. So they're sensed using different sense amplifiers. And this way you can actually get the highest capacity, because as we will see, low latency mode is going to replicate some data to get higher performance. So basically you get essentially the same storage capacity as a conventional open bit line architecture by enabling these type 1 transistors to mimic the connections as in the current architecture. So these transistors are disabled. Okay, that sounds good, right? Make sense? You'll need the paper to read the paper for more detail if you really want to see the exact open bit line architecture, but I'm giving you the high level abstraction. So of course you lose some capacity because of the isolation transistors, that they add some overhead, but hopefully that's not too bad, as we have shown in prior papers. Now, what is a high performance mode? That's where the novelty really comes in. Now here you enable both types of transistors. So both bit lines get connected to the sense amplifier above and sense amplifier below. And what you also do is you store opposite values. So if you store A over here, you store A bar over here. Now what this enables is, this is called a coupled cell. This enables the sense amplifiers to operate in a differential way. So you basically sense A as well as A bar. So that actually speeds up the sense amplification process in a single sense amplifier. That's one way you can reduce the latency. And also you can couple the sense amplifiers. Basically, both sense amplifiers are working in conjunction, like the linked precharge units that we have seen earlier, right? Similarly to that, both sense amplifiers are working together to amplify the charge. Because both two sense amplifiers together are stronger than one sense amplifier alone, you get additional latency reduction because of that. So there are two sources of latency reduction. One is because you're using these opposite values, and they enable a single sense amplifier to operate faster because you can actually do differential sensing. And the second is you're using two sense amplifiers at the same time. And that actually reduces latency. That also reduces the refresh overhead, which I'm not going to go into, but you can read the paper for more detail. So it essentially gives you a higher performance mode row. Of course, the downside now is your capacity is lower, right? Because you're using 2 bits to store 1 value. So you've held your capacity. This is a very fundamental trade-off, capacity latency. We've seen it in everything that we have discussed so far, actually. If you look at the tiered latency DRAM, we have a capacity latency trade-off, right? If you look at Crow, we have something similar. If you look at heterogeneous subarrays, we have something similar. Here we have something similar. I mean, it's the same trade-off, manifest in a different way. But they're manifest in different ways because the ideas are different, right? As you can see. And a lot of these ideas can be combined with each other. Actually, you can have a, let's say, kitchen sink, low latency DRAM architecture that combines all of these ideas. Okay, so let me give you the key results. Again, there's another paper that you can read for extra credit if you're so inclined. And the results look quite good, actually, because you can actually reduce many latency parameters significantly in high performance mode. Some latency parameters increase slightly in max capacity mode because of the isolation transistors that you add next to the sense amplifiers. But that trade-off we have seen before also. The trade-off was much worse in tiered latency DRAM, for example. And then you can read more in the paper. And the overall system level benefits, again, obtained using a system level simulation using RAMulator is also significant. I would say it's somewhat commensurate with past work. So it's not that different. If you can see, the values are kind of similar, like 20% range. But here you also get refresh energy reduction similarly to what we saw for Crow. That's not true for tiered latency DRAM. Tiered latency DRAM doesn't do anything for refresh. Okay. So this is a state-of-the-art work in DRAM latency. So if you want to improve stuff, I think we've covered everything in state-of-the-art in DRAM latency. Any questions, thoughts, ideas? Yes.
Sorry, I don't get why we like if you would.
Yeah.
I don't get why we have a DRAM refresh energy reduction.
Yeah. So basically now you have much stronger cells because you're coupling things, right? So one cell may be weak, but the other cell may be strong, right? So that is part of the benefits. There's some more, but it's discussed in the paper. So that's the beauty, right? Once you're coupling cells, you get actually a lot more benefit. So there may be even more ideas in DRAM refresh that this could inspire. Is Haosong here? He can answer some of these questions also. Yeah, but he's not. Yes.
Could we then maybe in a normal setup where we do the profiling and then we know where the weak cells are, use then this coupling to render these cells more
stronger. Yeah,
exactly.
yeah. That's a good idea, I believe. Yeah. It may be difficult to remap the cell on a cell level cell basis. Here you're basically coupling adjacent cells. But yes, I think that's a potential extension. There's a paper that was published in 2012. It's called Secret. That's essentially trying to do something like that. At a cell level, it's trying to figure out which cells are weak. And at the memory controller level, it's remapping them to somewhere else. So some part of that idea kind of exists in literature. It's relatively old. Yeah. Any other thoughts? Yes.
Yeah, this stupid question. How do they couple these two cells?
Okay, so basically that requires some modification that I didn't talk about, and that's not also fully covered in the paper. You store opposite values, basically. That's it.
So it's like you write a program and you read the data and then you reverse it and then
yeah, you can think of it that way. You complement it and then store it to the
same row.
Yeah.
Okay.
I mean, it doesn't. You have to store it in two rows, right? If you actually have, because you're reducing the capacity of a single row. Yeah. So there needs to be some mechanism to do that. Okay. That's part of some follow-up work that's not published. Yes, please.
This method introduced, well, from what I understand, they introduced. I'm using it, but I can. Okay, right.
Yeah, that's better. Mm-hmm. Only when you're reconfiguring, right? The overheads happen only when you're reconfiguring a row. But when you're reading, there's no additional latency in the memory controller. Right? Mm-hmm.
Which row you would like to copy and so on. So does this target heterogeneous computation, which might transit a lot of data, but then at some point you have very redundant data. So how robust is it to these kinds of?
I see. So if I understand you correctly, basically, which rows do you figure out to copy? Not necessarily here, but in the copy row, for example. Yeah, that requires some profiling mechanism to track, right? Which ones do you want to cache and which ones do you don't want to cache? That does add some overhead to the memory controller, certainly cost overhead, but you can hide a lot of the latency overheads. We will discuss memory controllers later, maybe today, but you can hide a lot of the latency overheads because while the memory controller is scheduling commands, you could actually do, let's say, decide which rows are better to cache in the background. That's a good question, though. All of these ideas actually require better memory controllers that do something to figure out which rows, for example, need to be reconfigured, which rows benefit from caching, etc. Okay. Okay, so let me give you an older idea. And this is actually interesting because there's a historical story about it also. This is one of the earliest works that we have done in changing DRAM, let's say, and we call it subarray level parallelism. It had a lot of, I think, nice impact on people's thinking about how DRAM should be designed. Like the subarray level parallelism, the subarray abstraction was not really thought of in the design of microarchitecture as much in the past before this paper. So essentially, the goal in this work was to reduce latency, but to reduce the latency of a bank conflict. So we're not going to reduce the fundamental latency, but we were going to reduce the latency that happens when you get a bank conflict. And what bank conflict is essentially when you have one request going to one bank, another request going to the second bank, and the second request gets serialized, right? It has to wait if it's going to the same row, if it's going to a different row. So clearly, these actually waste energy. They thrash the row buffer. They cause busy waiting, etc. Our goal was to reduce these bank conflicts without adding more banks, essentially low cost. Clearly, you can add more banks, and that reduces the bank conflicts. And people have looked at that. The observation in this work is essentially what I said earlier, right? The DRAM bank is divided into subarrays, and each subarray has its own local row buffer. And can we take advantage of it somehow? So this is what it looks like. Logically, this is the abstraction. Physically, we have these subarrays, as you have seen earlier in row clone, for example. But this work predates row clone and talks about how to take advantage of these subarrays architecturally in a different way. Clearly, these subarrays have been designed forever, right, in DRAM. But not many works have thought about how to take advantage of these subarrays architecturally in the memory controller level, because these are not visible to the memory controller. Before this work, people were not thinking about making them visible to the memory controller. Okay, so basically, the physical bank looks like this. You have a bunch of subarrays, and each of them have local row buffers. And that's where the sense amplification happens, as we have seen earlier. And then if you want to move some cache lines, you go to a global row buffer, which is not as large as local row buffer. This could be 64 bits to 156 bits. Local row buffer is 8 kilobytes, for example. Okay, and then the second observation is very important. The subarrays are mostly independent, but not completely independent. So essentially, they share some structures to reduce cost. So you have a global decoder that decodes an address, and only one word line gets enabled in one subarray. And then there's a global row buffer, which is essentially the global bit lines, as we will see in a little bit more detail. So if you want to actually reduce the bank conflicts, one idea is if two requests go to different subarrays, why not parallelize them, right? That's the idea of subarray level parallelism. Minimally reduce the sharing of these global structures. For example, if you reduce the sharing of the global decoder, you can enable almost parallel access to subarrays. And if you actually reduce the sharing of the global row buffer, you can utilize multiple local row buffers. So you can keep multiple row buffers active in a single bank, which is different from the abstraction that we have seen. So let's take a look at this. So I'm showing you two different subarrays in the same bank. And these are two different rows, blue and yellow. So instead of a global latch over here, so you have a global decoder. Normally what you have is you latch the address, which is a global address. This is a row address. And then the appropriate word line in the appropriate subarray gets enabled. So this address includes a subarray ID as well as the row ID in the subarray. So clearly, if your latch is over here, you cannot activate two rows, right? And the goal of this latch over here is to reduce cost by increasing the sharing, because people were not thinking about actually parallelizing requests to different subarrays. So instead of this global latch, why not push the latches and have separate per subarray latches? That's the idea over here. So if you do this, now you can send one row address to this subarray and then activate one row over here. And then immediately after that, you can send another row address over here and activate another subarray. So you can enable two consecutive activations, let's say, across different subarrays in the same bank. Does that make sense? Okay. So, I mean, you could do parallel also, assuming you send both addresses at the same time, but that's a tough thing because DRAM pins, DRAM address pins are not enough to send two addresses. You need to increase the pin count. So the proposal here is to send two consecutive addresses two addresses in consecutive cycles in DRAM. So that looks nice, right? Now, it doesn't completely work, unfortunately, as we will see, because there's a sharing of the global row buffer. But at least we solved the problem of two consecutive activations. Now we can do it. Can we do it reliably? No, because what happens in a current DRAM is you have these global bit lines. So I actually moved the subarrays. Normally the subarray is actually on top of the global bit lines, but just to make things easier to understand using the switch, we actually relocated the subarrays pictorially from here to here and here to here. Now assume that you've enabled two rows. You activated two rows and two different subarrays. Which one do you read from? Now, normally, you don't have isolation transistors or switches over here. So basically, normally what happens when you activate one subarray, they directly get connected to the global bit lines, so they start driving the bit lines, as we have discussed earlier. Now, you cannot do that right now, right? If you actually activate consecutively two rows and two different subarrays, they will be driving the same global bit lines because they're sharing the global bit lines, if you remember, and you'll get garbage values. Right? You don't want two different subarrays driving the same bit lines. So to disable that, you need to have a switch saying, I selectively enable which subarray is going to drive the bit lines. That's the idea over here. This is done using a designated subarray latch. It's a single bit per subarray saying, this is the subarray that's designated to drive the local bit lines. It's actually simple. It has some cost. Now, let's take a look at how this works. So these are the designated bits for each subarray. When you send a read, what happens is, this is a read that's to the blue subarray, as you can see. This switch gets enabled. Basically, this row buffer, these sense amplifiers get connected to the global bit lines over here, and the data goes out to the global I/O, global row buffer, essentially. And if you want to do a read to another subarray, you deactivate the designated latch over here, you activate the designated latch to this subarray, and that subarray essentially gets connected to global bit lines, and you can read the data from that subarray. Does that make sense? So it's very simple modifications, I would say, but no one has thought of these because no one actually had the idea of exploiting these underlying structure of the subarrays to improve parallelism in DRAM. And the benefit now, you can see hopefully the full benefit. Let me see. Of course, you need to be able to set the designated latch. So there's some overhead, as you can see. So the benefit is now you can activate two rows in two different subarrays, and you can switch between them. Meaning you're not trashing a single row buffer because you already have multiple row buffers in different subarrays. You can switch between the row buffers. That's the idea. So the overhead of actually bank conflicts have been reduced significantly in this particular case because you don't need to pre-charge the bank and reopen another row. Those rows are already open. You just need to do the switch operation, which actually takes very little time, as we have shown in the paper. So basically, what have we done? This is the baseline bank organization. In the baseline, you cannot open two rows, as we have discussed. We basically pushed the latches over here, and then we added the switches, as you can see. So there's some overhead, clearly. And in the paper, we actually estimated to be very low. I believe the overhead is a bit higher than what's estimated in the paper, but I don't think it's that high. And that's the idea. Now, for example, you can do this idea, of course, across, let's say, if you have 128 subarrays, you can open 128 row buffers in DRAM. Of course, keeping 128 row buffers active in DRAM consumes additional power because all of these are active. So your power consumption increases. In the paper, we analyze the trade-off, but you can read the paper for more detail. Yes?
Where's the switch in this picture?
So in this picture, well, it's not exactly shown, but it shows that this designated latch is connected. So this switch is connected to the global bit lines, but this switch is disconnected. So it's these red things over here. Those are the switch.
The switch and the latch are different.
That's right. Latch is what connects. Well, this latch is certainly different. Yes, you're talking about this latch, right? The latch is for the address.
Okay.
Basically, which word line you're driving.
Yeah.
That's the latch. Whereas switch is or this designated bit over here tells you which subarray is supposed to drive the global bit lines.
Okay.
Okay.
And the benefits of having two latches is because you can enable two subarrays at the same time.
Exactly.
And then the switch then the switch goes in subarray.
Yeah.
Line two.
Well, the switch enables you to choose which subarray is going to output the data on the global bit lines. So enabling 2 subarrays is not enough because you need to have a mechanism to choose which subarray to get the data from because they're sharing the global bit lines, right?
Oh, okay.
Yeah.
So the latch is opening 2 subarrays and the switch is choosing which.
Choosing between,
Okay.
choosing which data will get out, which subarray will send the data.
Yeah. Okay.
Okay, sure. Okay, so there's analysis in the paper, again, using Ramulator, well, an earlier version of Ramulator. But you can see that the energy reduction is actually significant because you reduce the row buffer conflicts. You reduce the impact of bank conflicts. And the system performance improvement is also significant. And according to our results, this is within 3% of ideal, meaning all banks are independent of each other. Well, all subarrays are independent, I should say that. Basically, you can think of subarrays as independent banks, right? But that requires a lot of overhead also, as you can see. So the die area overhead, as I said, is less than 1%. But if you actually enable all subarrays to be independent, you get significant overhead because you need row decoders for every single subarray, which we avoid over here. This paper actually has good analysis that you can take a look. There are different versions of SALP1, SALP2, and MESA. I'm not going to go into those. What I've described was the multiple activated subarrays, basically. It's the most aggressive version. But if you actually want to reduce the overhead, you can actually get less benefit and even less overhead, essentially. But I will not talk about that. So, okay, there's more on SALP, subarray level parallelism. Actually, I don't have the slide over here, but actually more recently, I have mentioned it earlier, but there's a work that we published at Micro that Giray led, which shows that you can actually do part of this in real DRAM chips. So in real DRAM chips, by violating the timing parameters, you can actually activate 2 different subarrays concurrently. So that actually reduces the refresh overheads and RowHammer overheads. This is a HERA paper that I will probably add it over here later on. Does that make sense? So real DRAM chips are actually capable of doing part of this. We actually always thought it that way, but it required 10 years to actually show it. Now, not that we worked on it over 10 years, right? It's like someone needs to come and show that, basically. You need to have someone with energy to actually show that this could be doable. We always thought, so basically, what HERA does is something like SALP1 or SALP1 or between SALP1 and SALP2. If you read the paper, you'll figure that out. Now, the interesting thing is this idea was found actually very, very interesting by 2 major companies, at least 2 major companies. But even then, they were not able to convince, let's say, the broader industry to adopt this idea, which I think is, in a sense, the nice thing is clearly this idea has a lot of impact, as I will mention. But unfortunately, it's not implemented today because of the way I believe the mindset and the business of memory industry works. It's very difficult to change things. Because I believe it's very backward looking in one sense, and it's very, let's say, conservative. So let me give you the story. Basically, this paper that I mentioned earlier, it was written 2 years later, our SALP paper was published. And remember that I mentioned this paper multiple times. This paper argues that you need to design DRAM together with controllers to overcome process scaling challenges. And part of this paper, these are slides, but in the paper also you can see, evaluates subarray level parallelism completely independently from us. And they basically say that this is a very good way of tolerating latencies, increasing latencies. So one of the problems with DRAM scaling is, which we didn't talk about that much, but write latencies increase. Why? Because the contacts in the access transistors becomes more resistive. As a result, when you're pushing data into the DRAM cell, your latencies increase as the access transistor becomes smaller. There's more information on this in this paper. But so in order to write data reliably into a much smaller cell, you need to increase the write latency. Now, this paper says, okay, we can increase write latency, and we should probably, because otherwise we'll run into reliability issues. But we can tolerate the increase in write latency using subarray level parallelism. And this is basically essentially the same idea that I described earlier. And this is what they show in the paper. And their results are actually somewhat similar to us. They basically say that, I think maybe they basically compensate the increase in write latency. So if your write latency increases by 5x, you still get improved performance using subarray level parallelism. I think maybe 3x. I don't remember. Yeah, they look at 3x. They look at 5x over here, but they look at 3x over here. So basically, even if you increase your write latency by 3x, you still get 3% performance improvement overall across many applications because you do subarray level parallelism. Because while you're writing to one subarray, the latency, even though the latency is high, the other subarray you can read or activate, right? That's the idea. So that write latency is not affecting you a lot. Unless, of course, both requests go to the same subarray, right? Now, if you go to the same subarray, unfortunately, this subarray level parallelism idea doesn't eliminate that conflict, right? That conflict is still there. Subarray level parallelism idea eliminates conflicts between requests that go to different subarrays or reduces the impact of conflicts. So clearly, these folks actually have done a lot of work to evaluate the idea independently. And they actually tried to convince the JEDEC, which is the standard, DRAM standard body, to actually implement this idea. Unfortunately, they have not been successful. That's why you don't see subarray level parallelism in the DRAM chips today. And I think this is because there's just too much difficulty in getting new ideas implemented in DRAM, unfortunately. It's changing. You can see that in RowHammer, ECC, some of the ideas actually have gone in, maybe not in the best ways, but this idea, I think at some point will come back. We'll see when it comes back. Yeah. Okay, any questions? Yes.
What's the main difficulty of implementing SL?
Okay, so the main difficulty, well, certainly you need changes to the DRAM. This also requires changes to the memory controller. Basically, this requires changes to everywhere. Well, everywhere, meaning memory controller and DRAM. In the memory controller, you need to keep track of which subarrays are active, right? And you need to add new commands. You need to change the interface to switch between subarrays. So it requires a lot of changes. And essentially, it's all doable. It's not that difficult, in my opinion. I don't believe that these are actually very difficult changes, but people are very resistant to change in general. Now, if you can do everything in DRAM, it's easier. If you can do everything in the memory controller, it's easier. But this changes the memory controller, DRAM, and the interface, right? So that's one of the main reasons why it's difficult to get some of these ideas adopted in the standard, at least. So if you want to do a non-standard DRAM, I think you can actually design your own controller on DRAM and do it, I believe. And I think more people should do it, frankly. The standard, at least the way business works, the way the standards are determined, it's a very political process. So if you look at, on one side, there are DRAM companies. On the other side, there are many memory controller companies that design memory controllers and sell them. On the other side, there are system companies like Microsoft, Google, etc. They also actually have a say. And also integrators like Apple. So there are many, many companies at stake. They basically go and discuss. And in the end, what you get is, oh, we don't want to change anything, usually. That's an approximation of the reality, let's say. Clearly, some change happens, right? But these changes are deemed to be extremely important, like RowHammer, right? People are now discussing RowHammer finally a little bit more in this set of companies. It's called JEDEC, essentially. You can be a member of JEDEC and become part of the discussions also. Actually, you can be a voting member if you pay enough. So essentially, a lot of people can be a member, and it becomes a very political process as a result of this. That's very difficult to change. For example, going from DDR3 to DDR4, I believe took at least 5 or 6 years. Going from DDR4 to DDR5 took about 8 to 9 years. So it's basically taking longer and longer to come up with a new DRAM standard. That's general purpose. Does that make sense? Yeah. So I think a lot of it it's the process to blame and the interface that we've kind of confined ourselves into. If we actually started with a better interface, maybe we wouldn't be in this situation right now, but that's how industry has evolved, right? It's a very, very coupled interface between the memory controller and DRAM. We're going to talk about that a little bit more when we talk about memory controllers. But everything is dictated by the memory controller, and DRAM cannot do anything. That interface is not flexible. As a result, it's very difficult to change also. Okay, hopefully that gives you some insight into how the industry operates in this domain. Now, that's the interesting part about like when you're communicating with devices, right? If you're designing your own chip and you're not communicating, you're not changing anything, you don't want to change anything around you. If you're designing your own chip, that's relatively easy to change, right? Because it's your own chip. But even then, if you look at a single company, within a single company, there's a lot of let's say, siloization, meaning some people are responsible for designing the core. Some people are responsible designing the cache hierarchy. Some people are responsible for designing the interconnect. Some people are responsible designing the memory controller. And if you want to change the interface between them, that's also difficult within a company. We're talking about within a company, right? Sometimes you want to change something, or people say, oh, that increases my cost over here in the L2 cache design, so I'm not going to do what you say. And you need to actually argue, fight, etc. Hopefully with data. Sometimes it doesn't happen with data also. So this sort of issue actually exists in even within a company. Now you can imagine how much more difficult this becomes if hundreds of companies are involved, right, in making a change. That's the difficulty of standardization, basically.
So
Yes.
So maybe the management need to have a global view and then enable to convince each part, like in the long term.
That's right. I think within a company you can do that, certainly, right? If you have a strong management that knows what to do and that can gather data from all of these, yes. Yeah, within a company it's easier to solve, but across companies you don't have that, right? Yeah. Okay. So similar things actually happen in the storage domain also, right? This is memory, but storage, once you go into storage, that interface is another interface, right? Those interfaces also change slowly. And there are other, there are similar issues basically. Okay, let's move to the next part, which is the second reason. Actually, should we take a break at this point? Any thoughts? Okay, let's take it. I think before moving on to the second reason, let's take a 10-minute break, because it's a good place to take a break. And then we'll continue with the second reason. Yes, I need to get back to you, yes. Hopefully this week, you're on the priority list, yes. Okay. Okay, let's get started. This is still working, that's good. Okay. So we've covered some microarchitectural changes to reduce latency. And you can see that a lot of these also reduce energy as well, even though they may have increased power, peak power, because you're enabling multiple things at the same time. So this is a very good direction to think about going into the future also. How can we redesign the microarchitecture or architecture of memory so that we can reduce latency as well as reduce energy? Now we're going to switch gears and talk about the second reason that's orthogonal, which is the way we approach latency, which is one size fits all. Essentially, we use the same latency parameters regardless of the temperature that the chips are operating at, regardless of the types of DRAM chips, regardless of the different parts of the DRAM chip, regardless of supply voltage levels, application data, etc. Basically. So there's a lot over here, and we're going to try to cover all of it. Let's see, with examples again, right? Again, as I mentioned earlier, a lot of these ideas are applicable to other memory types as well. We're going to look at DRAM, but people have found out that other memory types are also benefit from this sort of optimization that we're going to discuss. And also there may be more ideas. So it's always good to be on the lookout for new ideas here. So I call this a fixed latency mindset. Basically, if you look at it, reliable operation latency is actually very heterogeneous across different temperatures, chips, parts of a chip, voltage levels. Basically, if you want to operate reliably, you can set the latency differently for these different things, let's say. And the general idea that we're going to look at is to ideally dynamically, but find out and use the lowest latency one can reliably access a memory location with. That's the basic idea that we're going to try to achieve. Figure out what's the lowest latency you can access a memory location with under different operation conditions, and use that lowest latency as opposed to using a single latency for everything, essentially. And there are many, many ideas that we're going to cover. And some of these will actually lead to very, very interesting things also, like true random number generators in DRAM, physical unclonable functions in DRAM, etc. So to be able to do this, of course, you need to identify what are the sources of latency heterogeneity or difference in latency and exploit them to minimize latency or create some other benefits. Like in the earlier part of the memory latency lectures, we were talking about creating latency heterogeneity, right? Tiered latency DRAM, for example, creates latency heterogeneity in DRAM based on the design of the DRAM microarchitecture. This is very different from what we're going to do now. We're going to figure out existing latency heterogeneity in DRAM and exploit that. So you can always create heterogeneity or exploit what's existing. And one of the major reasons for heterogeneity is the heterogeneous manufacturing and operating conditions. That leads to latency variation in parameters. For example, this figure is a conceptual figure that basically shows that different DRAM chips have different reliable operation latencies. Some of them can operate at low latency. Some of them require high latency because of the way cells happen to be because of manufacturing variation, right? Some cells cannot require longer latencies to access data reliably from. And we will see the cause of that. Because of variations in the capacitor may be very small. In the access transistor may be very resistive. These are manufacturing non-idealities. You cannot manufacture every single cell equally. As a result, different DRAM chips may be different. And within a DRAM chip, also latency is very heterogeneous. Some cells you can operate at low latency. Some cells you have to actually operate at high latency. And these distributions can overlap also, as you can see. So basically, within a DRAM chip, you have slow cells versus fast cells. So why is latency high then, right? Because we don't distinguish between any of these basically today. We have a constant DRAM latency, which is delay as specified in DRAM standards. We'll see this more in the next lecture. Basically, you have different timing parameters. We've seen timing parameters before, actually, but we're going to see more of them. And this is defined in the DRAM standards, data sheet. When you buy a DRAM chip, you get a data sheet that says, this is the latency of activation, TRCD. And this is what your memory controller should obey. If you don't obey that, we don't guarantee correct operation. It may still operate correctly, but we don't guarantee correct operation, right? That's it. This doesn't reflect the true DRAM device latency. This reflects basically a contract, essentially. It's a contract between the memory controller and the DRAM chip. If memory controller obeys, you're guaranteed correct operation, hopefully. If you don't obey it, you're not guaranteed correct operation. That's it. But basically, imperfect manufacturing process leads to latency variation, as we have discussed. Different DRAM chips have different latencies. And also within a DRAM chip, you have some variation. So what do DRAM manufacturers do? Like, how do they set these latencies in the DRAM data sheets? Well, their goal, as we discussed earlier, is to minimize cost. So how do you minimize cost? You set the latency such that you don't throw away a lot of your DRAM chips. That's the idea. So you set your data sheet latency contract, basically, such that your yield is maximized. Well, if you look at this picture, if your goal is to maximize your yield, meaning minimize the number of chips that you throw away, you set your standard latency this way, as high as possible. That way, all your DRAM chips are useful. They all operate under those conditions that you contract for. That's the idea, basically. This is the real picture today, basically. So now I've given you what causes the long memory latency. Basically, you have conservative timing margins. So if you look at this picture, standard latency is here, but this cell can operate much faster. So you have a very large timing margin in that sense. So DRAM timing parameters are set to cover the worst case temperatures, and also basically all DRAM chips are supposed to operate at 85 degrees. I guess in some cases 95 degrees also. But common case, they don't operate that high. So there's some latency variation because of temperature. And also to enable a wide range of operating conditions like voltages, different voltage levels, etc. And also worst case devices, which is what the picture showed. The prior picture didn't show the worst case temperatures and operating conditions like voltage. But it did show the process variation, which is worst case devices, worst case cells. Essentially, you're trying to cover for the DRAM cell with smallest charge across any acceptable device. Basically, slowest DRAM cell kind of determines your latency so that you can essentially tolerate process variation at acceptable yield, acceptable cost. And this leads to very large timing margins for the common case. Now, let's try to understand this. Let's try to understand and exploit this variation in DRAM latency. And we've seen that DRAM store data as charge before. And we've also already seen that everything is charge-based, right? You activate a row, charge gets shared, you sense the charge in the sense amplifiers, and the sense amplifiers restore the charge. So these are all steps that take time. You need to sense the charge when you do the activation first, and then you need to restore the charge, and then you can pre-charge, basically. These are all things that take latency time. So let's take a look at this from a DRAM cell perspective. This is the charge in the DRAM cell. This is initially the cell is charged, the sense amplifier is pre-charged, which is VDD over 2. That's what this is trying to show. And these are the charge levels of the cell and the sense amplifiers. We're going to take a look at that. So if you look at over time, if you send and activate, what happens is the cell gets connected to the sense amplifier. It does charge sharing. So cell loses charge, sense amplifier gets a little bit of charge. This is the sensing part. At some point, the sense amplifier starts getting enabled because it sensed that something is happening. So there's timing circuitry that enables the sense amplifier. And sense amplifier starts amplifying the charge. That's the amplification, or this is called restoration of the charge. And hopefully it pushes the charge all the way to the VDD, which is the level of the cell. It may not be able to, because the cells are also different, right? But in theory, this is where you can actually access the cell. But in practice, we add a timing margin because of multiple reasons that we discussed, right? Because this curve looks different for different cells. And also, there's temperature dependence. So these are the main reasons for timing margin. Process variation, as we discussed, DRAM cells are not equal. And some cells are slow, some cells are fast. And this leads to extra timing margin for a cell that can be accessed faster, basically. I'm thinking of this as a cell that can store a large amount of charge, but it's really a cell that can be accessed faster. This is an abstraction, basically, because we're going to see something soon. So let's take a look at this difference over here. So if you think about the DRAM cells as same size, same charge, and same, then hopefully they should have same latency, right? But because manufacturing is not perfect, the reality looks like this. Cells are different size. As a result, they have different charge amounts that they can store. As a result, the sense amplification process works differently for each of them. And as a result, they actually have different latencies, different reliable operation latency. When I say latency, think of it as reliable operation latency. How long do you need to wait for the cell to actually get to a state that's fully charged, for example? Now, normally I'm ignoring something. You can actually read the cell when its value is restored by some amount that's above the noise margin. So it's actually somewhere over here, but to simplify the picture, we don't show that over here. Okay, so that's basically the reason why you get variation. Large variation in cell size leads to large variation in charge, which leads to large variation in access latency. Now let's take a look at this variation. It's not just about charge, actually. It's not just about cell size, but this is kind of an abstraction, as I said. If you look at the DRAM cell, it looks like this. As I mentioned in an earlier lecture, you have a huge capacitor that's etched into the substrate. It's a huge 3D thing, if you will. And you have this contact, and this the bit line, and this the access transistor, and the word line is usually buried in the substrate over here, which is not shown over here. If you look at a real picture of a DRAM cell, you will see that. This is kind of imitating the real picture. And when you access, what happens is you connect the essentially the cell to the bit line through the access transistor, right? So there are three things that are important here, which is the cell capacitance, contact resistance over here, and the transistor performance, right? They're all important for latency, actually. And a small cell can store small charge means really that you have small cell capacitance, high contact resistance, and slow access transistor. This is the worst case, basically. Capacitor is bad, let's say small. Resistance is really bad in the contact, and access transistor is also slow. If all of those are slow, that's probably your slowest cell. So some cells are exactly opposite, right? Cell capacitance is large, resistance is not high, resistance is low, and the access transistor fast. And these are things you cannot control. These are manufacturing variations that you have. And these variations actually increase as you reduce the size of the cells and the feature sizes. So unfortunately, these variations are increasing basically today. So basically, that's why a cell has high access latency, essentially. These properties all differentiate cells in terms of their reliable access latencies. So, okay, that was process variation. There's temperature dependence also, and we know that DRAM leaks more charge at higher temperature, and this leads to extra timing margin for cells that operate at low temperature. So if you look at room temperature, cells are cool. If you look at hot temperature, they're very leaky. So they've lost a lot of charge, basically. So cells that essentially cells that store small charge at high temperature, cells store small charge at high temperature and large charge at low temperature, regardless of their size. This is true because they leaked a lot more, right? In the hot temperature, they're leaking faster, which means that there's a large variation in access latency across temperatures. You can access the cells much faster if you're operating at lower temperatures because they've leaked less charge. This is true for fast cells as well as small cells, slow cells. And if you're operating at high temperatures, for reliable operation, you should really increase your latency parameters in general if you want to differentiate between these. But if you look at DRAM timing parameters, so that these are two sources of variation. If you look at DRAM timing parameters, these timing parameters are dictated by the worst case for the reasons that we discussed earlier to minimize cost, which is essentially the smallest DRAM cell with the smallest charge in all DRAM products, assuming that it's operating at highest temperature. Right? It's basically the really worst case. Of course, there's voltage here, assuming that it's operating at the lowest specified voltage, which I'm ignoring over here, but that also exists basically. So it's actually a little bit more complicated than what we're talking about, but we're not going to change the voltage over here. But that's actually something that may be interesting that we will discuss later on. So essentially, this leads to a huge timing margin for the common case, as we will see in real DRAM chips. Now, this is actually true for processors also. How many of you have designed any processor? Okay, some people. That's good. How many of you have done assignments in pipeline processor design, for example? Okay, that's good. More of you, that's good. So if you look at, even in those assignments, how many of you have calculated the critical path of a processor, of the pipeline design? Okay, now, if you know the critical path, the timing of a processor, the clock frequency of a processor is essentially determined in somewhat a similar way, right? You really find the worst case critical path under worst case conditions. You figure out what is the clock period that I can clock the circuit at under possible worst case conditions. You need to take into account worst case temperature, worst case voltage. If you're not taking that into account, then you're ignoring something important. And you also need to take into account the worst case critical path in your combinational and sequential logic delay. So that's just true for the processor also. Actually, in a processor, you can eliminate a lot of the margins if you're not operating in that under those worst case conditions. For example, people propose dynamic voltage and frequency scaling, right? You can actually increase your frequency if you're not operating at very high temperatures, right? Because you're not at the worst case. So that's an example of adapting your latency in a processor, frequency in this particular case, to the operating conditions. So basic idea in this work is why not do it for DRAM as well? Adapt it to the essentially adapt the latencies to the operating conditions and the variation. So in processors, the way people use variation is they actually bin the processors. So some processors can operate at high frequency because there's, let's say, transistors happen to be fast in that processor. So those processors are bin to be operating at higher frequencies. Some other processors where they have slow transistors by luck, let's say, in general, they're bin to be operating at lower frequencies. So in processor industry, this binning is already done. In DRAM, some of that binning is already done in terms of frequency, bus frequency, but not in terms of latency. So the latency binning is not done in DRAM that much because it increases the testing cost, as we will see. So there's a downside to it, but the benefits, I believe, are relatively large, as this paper shows. So basically, the idea of the paper is very similar to what we have just said for processors. Optimize the operation for the common case, not the worst case. Optimize the timing parameters in particular. What is common case? Basically, current temperature and current DRAM module. If you can detect these, you can actually do much better. So why would this reduce latency? Because of the reasons that we discussed, basically. In the common case, you have a lot more charge than in the worst case. And more charge in a DRAM cell leads to everything being faster. Faster sensing, faster charge restoration, and faster precharging. And essentially faster access in the end, including read, write, and refresh. Because refresh is all about activation and precharge, right? Sensing, charge restoration, and precharging. That's a refresh, basically. Okay, so let's take a look at this. I already said this, so I'll go through this relatively quickly, but sensing, you can sense cells with extra charge faster. That leads to lower sensing latency. Restoration, whenever you restore the charge, you don't need to fully restore cells with extra charge. So if a cell has actually a lot of charge, you can actually restore it a little bit less, reduce your restoration latency. Precharge, similar again. You don't need to fully precharge bit lines for cells with extra charge because cells are actually stronger. This is discussed in the paper. I'm not going to go into the details. But to be able to test this, again, this DRAM characterization infrastructure comes in very handy. Basically, you can actually test these hypotheses, and these are hypotheses essentially, whether they are true in real DRAM chips. And that's essentially what we did. And you know this infrastructure by now very well. So basically, we tried to check whether this faster sensing can lead to lower latencies. And out of 115 DIMMs that we tested, this are almost 1,000 DRAM chips actually, you can reduce the activation latency by 17% if you actually, by shaving the timing margins. There's a variation, of course. This is average across 115 times whatever chips, basically. Because some chips, you cannot reduce it that much because those are the, let's say, those are chips that have, let's say, bad cells, bad meaning cells that you need to access with high latency for reliable operation. But some chips actually you can reduce it more than 17%. It could be 35%. You can read the paper. The data sets are also online. But what you can basically determine operation latencies that lead to no errors. And on average, you can reduce this particular timing parameter significantly. Again, this is real results. Reducing restore time, similar. You can reduce the restoration time. These are charge restoration timing parameters, TRAS and T-write, write recovery. And you can significantly reduce those also, as you can see, without getting any errors in your system. Again, this is average. It's a distribution. And the paper also talks about precharge, which you can read. So now that it's demonstrated, you can actually do this in real chips. You can actually do it online as well. So this is the basic idea. We want to optimize the DRAM timing parameters or latencies online. And here, the proposal was to have the DRAM manufacturer to provide multiple sets of reliable timing parameters at different temperatures for each module. And the system monitors the DRAM temperature and uses appropriate DRAM timing parameters. So, yes, you have a question.
Because you talk about timing, latency, frequency, and timing margin, I guess, and charges, I was thinking, frequency means the refresh rate, right? And timing margin is a clock frequency, clock of DRAM, and then the latency is just the time you read the cell, the cost, right?
So in this case, I'm only talking about latency, actually. So I gave the example of frequency from an existing processor, like a CPU, just as an example, right? Because that's where the clock period determines your frequency. But here, we're just talking about the latency to access. Like this is the activation latency of a row, and this is the restoration latency after you do a read or a write. Yeah. And so we're not going to change the frequency, but you can also do that separately.
And this latency decides the DRAM frequency or something?
Latency, essentially.
Oh, okay.
Like how long you need to wait before you are sure that the data is in the row buffer, for example. Yeah.
This timing margin?
So timing margin is essentially how long you're waiting extra today because someone set that latency to be high.
Okay, so it's in the same scale of with latency.
Yes, exactly. Okay. Exactly. That's also latency. Additional latency that you're wasting today, you didn't need to waste, basically. Okay. So the basic idea, I mean, we've gone through this. Basically, so you monitor the DRAM temperature, and this is actually already done. There are temperature sensors on DRAM chips, and you use the reliable timing parameters for that temperature for a given module or chip. That's the idea. So it turns out actually DRAM temperature measurements are done in real chips, as we said. It's actually very hard to increase the DRAM temperature unless your DRAM is 3D stacked and stacked on top of your chip. Then actually your heat has nowhere to escape. So in a lot of modern SoCs, that's the case, unfortunately. Your DRAM and chip are stacked on top of each other. As a result, your temperature is high. But if you look at a desktop system or a server system and running in data centers, that's not the case. DRAM and chips are separate. As a result, it's very difficult to actually increase the temperature of DRAM, it turns out. And yeah, the previous works actually show that. There are interesting characterization studies that show that in data centers, DRAM is running at very low temperatures, etc. And some of the works actually try to maintain low temperature. We actually did a lot of work to try to increase the DRAM temperature in a 2D system, two-dimensional planar system. And it's very difficult to increase it beyond even 60 degrees Celsius, actually. So basically, the key takeaway is DRAM operates at low temperatures in the common case, in general. This may not be true if you're actually densely stacking things. So keep that in mind. So, and this is the latency reduction summary for if you're operating at 55 degrees Celsius. Basically, what I showed you earlier translates to a read latency reduction of 30%, 32%, as you can see, and a write latency reduction of 55%. So that's quite significant. Basically, today we're paying this is average again. Different chips have different values. Basically, this means that, in other words, you're using a write latency that's 2x, a little bit higher than 2x of what you can be using today on average. And read latency is a little bit over 1.33x, right? And this is if each parameter, we've already discussed this. So we evaluated this idea on a real system. In a real system, you cannot dynamically change the latency, unfortunately. It's not exactly the same idea. You can statically change latency in some systems. So this is an AMD system, for example. In the BIOS level, you can actually change the latencies. For example, the row precharge time or row activation time, TRAS and TRP. You can change those latencies statically in the memory controller. So you can violate them actually in a real system beyond the standard. And we did that, and we examined the effect on real workloads based on the DIMMs that we've tested. So based on the characterization that we've done for a module, we changed these parameters appropriately so that we expect we're not going to get any errors, right? And then you run real workloads, and then you don't get any errors. So it's not a surprise, basically, because we've tested on FPGA that we expect that we're not going to get any errors if we actually use these DIMMs at these lower latency levels because we rigorously tested them. Now you plug that DIMM that you've tested to a real system and run real workloads. I believe for, 1 month or so. You could actually do even more rigorous testing, right? And then you look at the performance improvement as well as errors. There are no errors. And the performance improvement, as you can see, is significant. This is single core. Single core doesn't exercise memory a lot, but there are some applications. This is GUPS's giga updates per second. It's actually a random access workload. So in a random access workload, actually, those are the ones that are actually quite sensitive to latency. This is not the most sensitive workload because it has some parallelism also. But you can see that the performance improvement is significant, especially on memory-intensive workloads. This is really average across 35 workloads. I believe these are the sample workloads over here. And if you actually do this, so basically you can improve performance on a real system without any errors. And if you actually do the multi-core evaluation, meaning you have the same, I believe in this case, 4 copies of the same workload running together, your performance increases even more significantly because you have more impact on memory, right? Because now there's a lot more, let's say, contention in memory. If your latencies are lower, you reduce the contention. As a result, you get higher performance improvement. And on average, we see 10%, even if you include the non-intensive workloads. So I believe that these non-intensive workloads are not that interesting because they're not exercising memory, right? They're hitting in the caches. Okay, so that's basically the idea. And there's also analysis that shows that reducing the DRAM latency, the way it is as described, reduces DRAM power consumption as well. That's another example where reducing latency is good for power. And the reason is, this is just one reason, right? You reduce the row activation time, right? You're keeping the word line active for shorter. As a result, you're not driving the word line with high voltage for too long, and that reduces your energy and power consumption. That's true for precharging and restoration as well, but that's not analyzed in the paper in a lot of detail. Make sense? So we've covered some advantages and disadvantages of prior work, but let's discuss the advantages and disadvantages more clearly over here. It's a very simple mechanism, actually. It gets significant system performance and energy benefits, even on real systems, as we discussed. And benefits are higher at low temperature. A good reason to operate your systems at lower temperature. And low cost and low complexity, actually. By the way, this low temperature is interesting because people are trying to design quantum computers today that operate at really, really low temperatures. Unfortunately, there's no memory solution for quantum computing. Quantum computing is just about computing, not about memory. So the big elephant is still there, which is, what do you use for computing? You use for DRAM, right? If you actually use DRAM under quantum computing conditions, maybe actually you get reduced latencies. I don't know. It's actually good to think about it. Your refresh actually reduces also. Okay. So this is also low cost and low complexity. But disadvantage is you need to determine your reliable operating latencies for different temperatures and different dips. So in the end, the disadvantage boils down to higher testing cost a lot. How do you do that? You need to test a lot, basically, a lot more than today. Because today, you basically set your latency comfortably enough. You can basically say, oh, I don't expect my latency to be this high, but let me add a little bit more margin to it. Oh, 60%. That sounds good, right? So basically, you add a lot of margin today, which kind of gets you away from the testing cost, right? So there's a trade-off over there also. And this is an interesting trade-off between cost and latency. Again, a different way of thinking about it, because here you basically get rid of some of your testing costs. You still need to test some so that you gain some confidence and add some margin to what you've seen and don't test a lot. But here, you need to test a lot, basically. Now, again, the ideas that we discussed earlier can apply, meaning, do you need to do this testing offline or online? Actually, I believe that online testing is a lot better. Over time, you figure out. I think online testing is in general much, much better than offline testing, because if you do offline testing, you have to guarantee the timing parameters are correct after you ship them, because you're not going to do any online testing, right? So that requires a lot of cost. And as we discussed in an earlier lecture, most of the time that's spent in designing a memory chip, as well as a processor chip, is actually in testing and verification and validation. So if you look at DRAM, that's about 80% of the time. If you look at processors, I believe that's getting close to 80%, actually. It's definitely more than 50, 60%. So testing is actually extremely important in modern systems. But even then, even though people dedicate 80% of the time for testing, you can see that RowHammer type of issues sneak in or sneak out into the field, right? Yes, please.
This testing is costing manpower, right? Or time, or in the design phase, or after design in the manufacture phase?
Well, this is after design. This is testing after design, because you need to look at the manufacturing variation and temperature dependence. It's costly in terms of, I mean, certainly manpower, yes, but it's really real time, because you manufactured, let's say, 1 billion chips, and you need to test all of them basically to figure out where they are, because everything has a different variation. So that's one. That takes time. If you want to parallelize this, you need to have tester testers, so testing devices. So you need to actually have many, many testing devices. And in real DRAM testing devices, actually, these are actually very heavyweight testing devices that people use that can change the temperature, voltage, etc., with very precise ways. So that actually is costly also. So cost comes from time as well as these devices that you need to, let's say, purchase or devise so that you can actually do the testing in parallel as much as possible.
Okay, so you're saying the latency is different for every chip.
That's right. Yes, exactly.
Okay.
Yeah. So basically doing this online actually can help a lot. And we're going to see how you can do it online and automatically. Okay. Low temperatures, of course, at low temperature, everything is easier, right? The problem is actually really high temperatures and low voltage. So these corners where you have very high temperature and low voltage, those are the parts that you need to really worry about. Okay, there's more in this paper. There's a lot more data, actually. You can take a look. So, okay. So if you look at ALDRAM, adaptive latency DRAM, this exploits two types of latency variation across time, meaning different temperatures, and across different chips. And both are costly. Now, the question, of course, maybe after this immediately becomes, is there other type of latency variation within a chip? And that's the next question we asked across different parts of a DRAM chip. So I'm going to talk about that next. And the answer is yes, of course, as you expect, right? There's variation everywhere, as we have seen. So this is another study that we have done. This is going to show essentially the same thing as adaptive latency DRAM here. Basically, we studied lots of chips. You can see 240 chips. We're reducing the activation latency. Standard is 13.1 nanosecond. But you can see that there are no errors. So this shows you the real timing margin. There are no errors until you get to, let's say, 10.0 seconds. The reason this is plotted in the granularity of 2.5 nanoseconds is we cannot test below that granularity. That's a limitation of the FPGA-based testing infrastructure that we have. I think we reduced that granularity today, but at the time it was 2.5 nanoseconds. As you go to 7.5 nanoseconds, now you get a variation, right? You can see that some chips have a very low bit error rate. Some chips have a very high bit error rate. So there's a huge variation. As you keep pushing latency lower and lower, a lot of chips start failing, as you can see. So this shows what I showed you earlier in a different way. There are different characteristics across different modules. So, but if you push latency too low, you'll get errors everywhere. And this bit error rate is 10 to the minus 2 means that you get 1 bit error every 100 cells, which doesn't sound good, clearly. Okay, but we've seen this. Now the question is, is there a variation also within a chip? Where are these errors within the chip? And if you look at one particular DRAM chip, one DIMM over here, at 7.5 nanosecond activation latency, which is basically one of these data points over here, and at 7.5 nanoseconds, yes. And if you plot the cache lines, some number, and the row, this is not all of the rows in the chip, clearly, some part of the bank, let's say. And if you plot the bit error rate, the probability that cache line will have more than at least 1 bit error, basically, most of it is white. Basically, most of the places don't have errors, but there are some errors that are clustered. So this shows that there's some spatial variation in the errors. Most of the chip is actually still okay, but there are some places where you get errors. The question is, if you can determine what are those places that you get errors, maybe you can do something in the memory controller, right? That's the idea over here. So activation errors are concentrated at certain columns of cells. And that's the idea over here. This is a difficult to implement idea, slightly difficult, but if you actually can implement it, you can gain more benefit than what we have discussed. The observation I showed you, this is an empirical observation. This is real, and the paper has a lot more data on other modules. And it proposed a design that's called flexible latency DRAM, FlyDRAM. It's essentially a memory controller-based design. You divide the memory into regions with different latencies, and memory controller uses lower latency for regions with slow cells and higher latency for other regions. Now, there's some overheads here, clearly. First, you need to do the profiling that we discussed within a chip. Obviously, that's high cost. We've discussed that. But you also need to have storage in the memory controller saying which regions are lower latency, which regions are higher latency. And those need to, of course, stay constant. Hopefully, they don't change. So your profiling needs to be accurate. So there's some overhead. Assuming that you can bite this overhead, let's take a look at what those regions could be. So this is the baseline. Everything has to be accessed. This is the baseline with row activation latency. Remember, the standard was 13.1 nanosecond. It's rounded down to 13 over here. So all cells need to be accessed for at 13 nanoseconds. And TRP is the row precharge latency, essentially. And you can see that these are profiles of 3 different real modules. You can see that in real modules, none of the cells need to be accessed 13 nanoseconds. In this particular one, D1, most of the cells should be accessed with 10 nanosecond latency for precharge also. And these are the fractions that can be accessed at 7.5 nanoseconds. So if you look at this module, for example, it's quite reliable, or it's quite fast. 99% of the cells in this module can be accessed at 7.5 nanoseconds. So by nature, this is a faster module, if you will. And this is a different module that's less fast, but it's still faster than what your standard DRAM latencies require you to do. So this shows, I think, that you have different profiles of the real DIMMs, and you need to accommodate them differently in the memory controller. So you need to identify which cells can you access at what latency. So that's the complexity of the issue. But assuming that you can do that perfectly, well, clearly this is the upper bound, right? Well, this is a, I guess, somewhat realistic upper bound, assuming that all cells can be accessed at 7.5 nanoseconds. It's not the ultimate upper bound, which should be 0 nanoseconds probably, right? That's the ideal. Ideally, you would take 0 nanoseconds, but that's kind of an unrealistic upper bound. Here is a more realistic upper bound, assuming that everything can be accessed at 7.5 nanoseconds. You could imagine getting here. How do you imagine getting here? 99% of the cells can be accessed 7.5 nanoseconds without any error correction. Maybe I protect the 1% with error correction, and they can still be accessed reliably at 7.5 nanoseconds. But I cannot imagine getting to 0 nanoseconds, right? How do you do that? If you can do that, then you can make a lot of money probably. Or you can write the next best paper, let's say. Okay, so these are the profiles. Now, if you actually take these profiles, these are obtained using real FPGA-based infrastructure. If you actually obtain, if you take these profiles and simulate them using simulation infrastructure and run real workloads, these are the benefits you get. Basically, in this module that has, let's say, that's a little bit slower, you get some benefit, which is 13.3 performance improvement, average across 40 workloads. In this slightly faster module that has more cells that can be accessed at 7.5 nanoseconds, you get higher benefit. And the module where 99% of the cells can be accessed at 7.5 nanoseconds, you get even higher benefit. And this gets very close to the upper bound, as you can see. So you can approximate the performance of the upper bound, but now your performance depends on what kind of module is in your system, right? So there's some performance variability that you introduce. For example, I mean, this performance variability already exists, I think, because of the way process variations exploit in the CPUs, but this amplifies the performance variability. For example, all of us who have the same phone, all of those phones are accessing memory at the same latency. But now, if I'm lucky, I'll get 20% additional improvement. If you're unlucky, you'll get 13% additional improvement. And maybe if you're really unlucky, you'll get somewhere around here, right? So that happens. So there's some performance variability. I don't believe that's a huge deal because there's a lot of performance variability that already exists, right? Anyway, so basically this is what you get if you exploit spatial latency variation within the DRAM chip. As I said, this is harder to exploit, but you can actually get even higher benefits here. Yeah, this is harder to exploit, even higher testing cost and more complicated controller. Could be very complicated actually, but let's not get into that right now. We're going to talk about controllers later. Any thoughts? Questions? Comments? Okay, let's keep going then. So I'm not going to talk about this work, but this work actually has a lot of observations that puts a lot of things together and makes some new observations about latency we don't have time to cover. This actually, for example, answers some more questions rigorously. Like, if you determine the latency of a DRAM cell, does it stay constant? Or does it change? Does it fluctuate? In other words, remember in retention time, we saw the phenomenon variable retention time, right? If you keep testing a DRAM cell, you'll see different retention times. Does the same thing happen for latency? If you keep testing a DRAM cell, do you see different reliable operation latencies? And the answer is basically no. You don't have this variable latency phenomenon, which basically makes it a little bit easier to exploit some of these techniques that we discussed earlier. The paper also shows that you can actually reduce the write latency significantly by more than 80% in existing DRAM chips. I'm not going to talk about that. And also it has interesting observations like this, basically. Basically, you can reverse engineer the DRAM chip by reducing the latency and inducing and looking at where the errors happen. So if you, this is an example. Basically, this shows that where the activation errors are if you reduce the latency a lot. And basically, you have a profile of the subarray, right? This looks like this subarray is a bit different from this subarray, right? So now you can actually determine the subarray boundary by looking at this picture. So you can actually reverse engineer what's going on in the DRAM chip by figuring out where the latency, where the failures are when you reduce the latency quite aggressively, and looking at how it maps to the picture. So you can determine the subarray size. You can determine a lot actually in DRAM by reducing the latency and observing the errors that you see. Okay. So, okay, the next question is, why is there a spatial latency variation within a chip? At least some of the reasons. Let's look at that. So basically, part of the latency variation is because there's some design-induced variation that naturally leads to portions of the DRAM chip to be lower latency versus higher latency. And this is because of the way things are designed, basically. This is an abstraction, but it's a good enough abstraction. So if you look at a DRAM subarray, you have word line drivers. This is essentially, you activate the row and they drive the row, and then sense amplifiers. We've discussed these before. Now, across the row, if you're far away from the sense amplifier, across rows, if you're far away from the sense amplifier, you're naturally expected to be slower, right? Because it takes time to propagate across the interconnect. So these rows that are closer to sense amplifiers are faster. These rows that are farther are slower. And a similar effect exists across the columns. If you're closer to the word line driver, sensing becomes much faster because, again, your interconnect delay is lower. If you're far away, you're slower. So just by looking at this picture, there's some part of a DRAM subarray that's inherently fast, and there's some part of a DRAM subarray that's inherently slow. So you can figure out this part actually by reverse engineering also. That's the beauty. Or someone can tell you, right? If the DRAM manufacturer knows the design, they can tell you. Now, if you know this information, you can actually do a lot of things, as we will see. Now, unfortunately, this is not the full story. So this is a systematic variation that happens because it's caused by because of the physical organization of DRAM. Now, internally, this looks a little bit different. You have word line drivers, but it's also divided into, a subarray is actually divided into what's called mats. So you have sub-word line drivers, but I'm not going to go into that abstraction level. The paper discusses that abstraction level. But this picture remains essentially. If it doesn't remain within a subarray, it remains within a mat, depending on how you organize things internally. So based on this observation, the paper proposed an online profiling mechanism to determine the latencies. The idea is this, basically. You know the inherently slow portion. Just profile that part of the DRAM chip to figure out what's your reliable minimum operation latency. Profile only the slow regions. Now that sounds great, right? If this was a full story. Unfortunately, well, this is good because you don't profile every single thing in your DRAM chip. You just focus on the inherently slow regions that you know are inherently slow. But unfortunately, it's not the full story because part of the latency variation is what we have discussed earlier, right? Which is there are some slow cells because of process variation. Now, we discussed this already. Because they're slow because they store less charge. Small capacitor, high contact resistance, poor access transistor, slow transistor, right? Now, the good news is these are kind of randomly distributed. If you actually look at where these cells are, they're randomly distributed. Now, based on what you have discussed in these lectures so far, there's a way to profile this and figure out the lowest latency over here. Now, what do you do with the slow cells that are randomly distributed? Random errors, error correcting codes, right? So basically, that's the idea. Find a latency based on the inherently slow region. Assume some error correcting code. If your error correcting codes can correct the errors in the other cells, assuming the latency that you found using the inherently slow thing, inherently slow cells, that's good, right? So hopefully this works. Add some margin also. You can always add margin, right? If for some reason you get more errors than your error correcting code can correct, either strengthen your error correcting code or increase your latency that you found using the inherently slow cells. So basically, you can actually do this dynamic profiling assuming some error correcting code. So that's the idea. And you can use online profiling and error correcting codes together to find a good latency where you will not get any errors. And you can design a mechanism. That mechanism is described in the paper. Now that's the beauty of this work, I think. This is actually quite reliable because it doesn't just rely on static profiling. It says, I'm going to dynamically profile. I'm going to focus on latencies based on this and see if my error correcting code works in other parts. If they don't work, then you start increasing your latency. And this way, actually, you can reduce your latencies even more significantly than adaptive latency DRAM. You can see these are the reductions that you see for read, and also at high temperatures. Because high temperatures, now you have error correcting codes that are naturally correcting errors that occur at high temperatures. Still, there's a difference between low temperature and high temperature, but it's not as bad as an adaptive latency DRAM as we discussed, right? Because that exploits temperature dependence, but it has no error correcting codes. So the reason you can get higher latency reduction is because you're using error correcting codes to profile. And write latency reduction is also high, as you can see. Okay. Any thoughts? Now this is more complicated, but now this is a more complete mechanism, meaning you do it online. Clearly, there's some online profiling overhead, like we discussed in retention time profiling. It's a little bit different type of online profiling overhead, but hopefully you reduce the online profiling overhead by by concentrating on the inherently slow regions. Yes.
I saw latency is about timing, but ECC is about correcting wrong code, right?
Mm-hmm.
How does it correct slow cells?
So latency is about timing, right? Basically, you reduce the latency. If you reduce the latency too much below the reliable operation latency of a cell, you get an error. An error correcting code can correct that. So there's a trade-off between latency and reliability. And you can always make up for the reliability loss because you reduce the latency too much by adding error correcting codes.
How does error correcting code know that's caused by latency?
It doesn't know. That's the beauty of error correcting code. You added some redundancy. If you get a bit flip, so basically from the perspective of an error correcting code, you have a bit flip. But because of the redundancy in the way you encoded the data, you can correct for that bit flip. Makes sense, right?
And this ECC is about every cell.
Yes, essentially it protects every cell. Yes. That's a good point. Yes. Yes.
Do we know the average, like, is it like the average ECC, I don't know how to say it, but like needed? So is it a 2-bit error correction code or a 3-bit or?
Yeah. I mean, in this paper, we look at single error correcting codes and double error detecting codes. But of course, you can make the latency reduction more aggressive if you actually make your ECC higher. We didn't. I don't believe you looked at that in this particular paper, but that's a very good question, basically. So just like there's a trade-off between error correcting codes and refresh, right? You can reduce the refresh rate by adding more error correcting codes. You can reduce the latency by adding error correcting codes. Okay. So we discussed. Well, I guess I already kind of said this, but it automatically this proposal, DIVA DRAM, design induced variation aware DRAM, automatically finds the lowest reliable operating latency at system runtime. So this gets rid of the production time testing cost, which is actually a huge problem, as we have discussed earlier. And it reduces latency more than prior methods by using ECC, of course. So there's a cost it adds. And it reduces latency at high temperatures as well. So it's more across the board, if you will. Now, unfortunately, it requires knowledge of inherently slow regions. Either the DRAM manufacturer or somebody needs to provide this, basically, or you need to reverse engineer it, which is possible. It's not that hard, actually. If you look at the paper, these regions are very clear. You can actually look at the failures you get based on different latencies, and you see that there are inherently slow regions in DRAM. It requires error correcting codes. That's part of the overheads. And it does impose overhead due to runtime profiling. And we've discussed this clearly. Ideally, you would like to reduce this. But having a small region to profile or focus on reduces that runtime profiling overhead also. That's evaluated in the paper. And as always, there's more complicated memory controller because it needs to be capable of at least profiling here. And basically deciding what latencies to use based on the error characteristics and the correction that you get. And that's the paper. Okay. We're not out of ideas yet. And I don't believe there will be out of ideas. If you keep discussing or thinking, there will be more ideas, I think. Maybe even bigger ones. But this is a more complete picture, if you will. Now we're going to switch gears over here and look at something completely different before I go into supply voltage levels. This is, I think, very interesting because today, even though the applications may be quite tolerant of errors, we're using the same latency parameters for all application data. But we know that there are some applications that are quite tolerant of errors. Neural networks are an example. And that's essentially what we're going to look at relatively quickly over here. Again, you can review this paper for extra credit. But clearly, neural networks have been very popular. It turns out large neural networks, especially large neural networks, access memory a lot because cache hierarchy becomes not so useful, depending on neural network type. Especially some neural network types like long short-term memories and transducers are actually pretty intense. But essentially, some data and layers and deep neural networks are very tolerant to errors. And you can reduce the DRAM latency and voltage on such data and layers. So you get more errors, basically, but you access things at reduced latency. Hopefully, this is OK, because in the end, you get the correct output. Now, you can do similar optimizations for video, right? If the end user doesn't get affected by your optimization, you get bit flips in the screen. But if they don't see it, for example, that's perhaps fine, right? You can do this in image. And image and video, this has been used because these are thought of as error tolerant applications. Of course, you need to provide some quality of service to the user so that they don't get affected, right? Similarly, in neural networks, as long as you achieve some amount of accuracy, you can play games with the errors that you get because they're tolerant. So that's the idea, basically. You can reduce DRAM latency and voltage on error-tolerant layers based on the error tolerance level that they have, while still achieving a user-specified accuracy target. And how do you do that? You can actually make training of the neural network error-aware. And that's what the proposal is in this work. You can think of this as data-aware management of DRAM latency and voltage for neural network inference. So let me give you an example. This is from one neural network, deep neural network, ResNet50, which is commonly used. And this shows the different weights and input feature maps of the neural network. And you can see the maximum tolerable bit error rate in the weights. These are essentially different parts of the neural network. And you can see that some of them are quite error tolerant. Let me actually do this. For example, these weights in this particular case can tolerate error rates that are quite high, like almost close to 10% in this particular case. These weights cannot tolerate error rates that are higher than, let's say, I don't know, like this one cannot tolerate higher than 2%. And you determine this by injecting errors and looking at the accuracy that you get. So there needs to be a process where you determine which weight gets affected by how much by injecting errors. So there needs to be some error injection to classify what weights are tolerant errors and what weights are not tolerant errors, or by at what level different weights and different inputs are tolerant errors. And you can classify them this way. And let's assume that you classify them into 4 bins. These are, this is a bin where you get at most 2% bit error rate. This is a bin where you get at most 5%. This is a bin where you get at most 6%. And this is a bin where you get at most 8%. And you can basically set your DRAM voltages and latencies such that you obey these maximum bit error rates and map these different layers to different DRAM parts. That's the idea. Map more error tolerant neural network layers to DRAM partitions with lower voltage and lower latency that essentially satisfy the bit error rate requirements of the things that you group. And here we group things equally because we're assuming that they're occupying the entire DRAM, for example, right? You have 4 different partitions. So that's the idea. You set your DRAM voltage and latency and determine your bit error rate such that it satisfies the maximum tolerable bit error rate of the weights that are going to be mapped there. I'm not going to go into the details, but this actually is an iterative process. You need to characterize your DRAM error profile. You need to characterize your neural network. And you need to do the DNN to DRAM mapping. And then you need to simulate to figure out whether you have good accuracy. If you don't have good accuracy, you need to retrain your neural network based on the profile and boost it. So there's a training process that's error tolerant, based on error characteristics that you see in DRAM so that you can actually get better accuracy with the mapping. So it's an iterative process, and it's described in the paper. This is already done actually in neural networks in different ways, not necessarily for DRAM, clearly. That's why this is new. But it's done, for example, if you want to prune your network in some way, you want to get rid of some of the weights in your network, you basically figure out which weights don't matter as much, and then you remove them, and then you lose some accuracy. And once you lose some accuracy, you retrain your network so that you recalibrate and maybe add some more weights somewhere or put them back. So basically, this is already done in neural network training today, so that you can actually reduce the size of your network, for example, especially if you want to fit the network to an embedded device. You need to do something like this. Except the difference over here is you need to take into account DRAM errors. The errors are not coming because you're compressing the network or removing some of the weights or quantizing some of the values to reduce cost. The errors are coming because you're actually mapping things to an erroneous or approximate memory. Okay, does that make sense? Okay, if you've done neural network training, you probably know. How many people have done neural network training here? Okay, so does this make sense? Okay, how many people use quantization, for example, in neural network training? Okay, I see a lot of hands, so hopefully you've seen this before. So think about not using quantization, but using erroneous DRAM as injected errors. Okay, so it turns out this improves energy significantly. I mean, it's a trade-off between energy and accuracy. In the end, we didn't try to, the paper has more results, but if you actually are tolerant of accuracy a little bit, accuracy loss a little bit, you get a lot more benefits. So you get 21% DRAM energy reduction while maintaining accuracy within 1% of the original network. And also a system speed up, as you can see. I'm not going to go through the details. Basically, this reduces your latency as well as energy. And this is evaluated also on a GPU and machine learning accelerator like TPU, tensor processing unit. And you can see the energy reductions are actually quite significant. And you can read the paper for more detail. But this is an example of using the characteristics of the application data to reduce your latencies. And again, it's another example of reducing your latency, reduce your energy. Right? That's a very common theme, basically. Okay, any other questions? Okay, there's more, and you can read or watch more. But this is a general. If you look at this, this is. I think we discussed this actually because there was some question in an earlier lecture. This is a specific mechanism that takes advantage of error tolerance of applications using heterogeneous reliability memory. So you have essentially heterogeneous reliability portions of DRAM. They offer you different reliability, and you map your data appropriately to different portions so that you can improve some metric. So this idea is actually relatively old. So in the general sense, you can characterize your application and data, and you can basically find memory error vulnerability. For example, this data is not as vulnerable to errors. If you get bit flips, for example, in your data, you don't lose that much correctness. Here, you may be completely vulnerable. You get completely useless results, right? So if you can characterize your application such that in the abstract way, some data is vulnerable, some data is tolerant to errors. And you can imagine different shades of gray over here, right? Like we did it with Eden. It's not like vulnerable, tolerant. It's not black and white. It could be different error rates, for example, tolerable error rates. Now you can map your data to different types of memories. In this particular case, another example is you can have very reliable memory that's high cost, and you can have not so reliable memory that's low cost, right? And if you do the mapping, you can actually save some things. So there is actually a huge design space over here. This reliable memory can be protected with error-correcting codes, maybe very well-tested chips, for example. It could employ many, many mechanisms over here, whereas here, maybe you don't care as much. No error-correcting codes, maybe some parity error correction, I don't know. Less tested chips. So you can actually reduce the cost of this significantly. And we call this heterogeneous reliability memory. I'm going to mention the paper that was published in DSN some years ago. But we actually did a lot of testing with this sort of idea together with Microsoft. And on some workloads, this works really well. For example, in data centers, you can eliminate ECC from most of your memory. You can reduce the hardware cost in a data center while still achieving good availability in a data center. You can read the paper for more detail because hopefully you've identified your vulnerable data well, such that you mapped it to reliable memory. Now, in practice, it's not as easy to do. I should admit that it's not very easy because, first of all, you need to be able to identify your vulnerable data very accurately. If you make a mistake, then your application crashes, for example. Not a good idea, clearly. So you really need to be running very tolerant applications. I think neural networks fit this nicely, but neural network not under safety critical conditions, I would say. You may have a neural network that's not so safety critical, right? I don't know. It can recognize my voice, for example, and translates it. If it gets a couple of words wrong out of 1,000 words, maybe it's okay, right? As long as those are not critical words, of course, right? Or maybe you may have, hopefully, an error correction mechanism. So it depends on the application, basically. I think web search is similar to that sort of application because people can tolerate errors once in a while. And maybe you can, at the higher level system stack, you can actually make this work for web search even better because web search is a distributed system problem, right? You can actually reduce your cost by, actually, there's a lot of redundancy that happens in web search. You send a query and there's a lot of queries that go to multiple servers and multiple servers respond today. So there's a lot of redundancy in the search. It's not just a single query going to a single server. So that redundancy can enable this sort of mechanism at a data center level. So that's why web search is not a bad application over here. Because there are some distributed system level mechanisms that lead to redundancy. It's not just a single query getting service from a single place. And if you get unlucky, you'll get the wrong results. Okay, so basically the general idea is heterogeneous reliability memory. You can think of this as many applications and many different data. And you characterize and classify the error tolerance of different data and applications. And it's a continuum, as you can see, or different error tolerance levels. And you map application data to the heterogeneous reliability memory system using software-hardware cooperation. And then there's a design space over here, clearly. How do you design the heterogeneous reliability memory system, right? There's a huge design space, actually. What are the techniques you employ for unreliable memory versus reliable memory? How do you guarantee different error rates? I think guaranteeing different error rates is going to be important. Because even unreliable memory today is not, reliable memory today is not perfect memory, right? There is an error rate that's guaranteed. Usually it's 10 to the minus 15 or something very low, basically, 10 to the minus 16. So it's really about guaranteeing some error rate. And usually these guarantees are probabilistic, as I just said. The error rate is guaranteed. So there's no I think you cannot guarantee a perfect memory in general. Okay. So you can see that this idea actually is very, Eden is one incarnation of this idea, that deep neural network mapping to different DRAM regions is one incarnation of this idea. I believe there's a lot of incarnations of this idea, and it's a huge design space to explore. This paper explores some of that design space, but it doesn't, I think there's more to explore over here. Any questions? I feel like you guys have been silent for a while. Thoughts? But this is actually interesting in another sense. It actually enables more scalable memory system, right? If you look at the system, if you can make your reliable memory as small as possible and low-cost memory as large as possible, now you can, maybe you don't care as much about some of the technology scaling issues, right? Now, you need to be very careful with that, but I believe this actually enables a more scalable memory system if it can be done in a nice way. Most of your memory is low cost, a fraction of it is reliable, and it solves the technology scaling issues at very high cost, potentially, but you don't pay the cost for those memory technology scaling issues over here. But the way you're doing that is by taking advantage of the application characteristics. So if your application is completely intolerant, you cannot do this clearly, right? So by definition, by design, this doesn't apply to all applications. I don't want this in my self-driving car, let's say. Let me put it that way. Or in my airplane controller, right? Forget about it. I'll pay the cost of safety. Okay. Okay, so that was a different direction. Let's talk about voltage a little bit, because it's also another aspect of latency as well as power. And now things are becoming a little bit more complicated, right? Latency has effects on reliability. Now voltage has effect on reliability, but voltage and latency also are coupled together, and they have a combined effect on reliability. And we're going to take a look at that. And this is a paper that analyzes for the first time, as far as I know. And one of the reasons why we looked at this was because of the huge power consumption of DRAM. This is actually old data. You can see that in real IBM power systems, 40% of the power, system power, is spent on DRAM. In real NVIDIA systems and GPUs at the time, you can see that the values are actually old. These numbers are increasing. 40% of the power is in the GPU. Today, actually, that number is over 50%, I think. And system cost is also similar, right? Most of your system cost is actually DRAM, especially if you look at a data center. So the question is, how do you reduce, let's assume that you have the voltage lever. If you reduce voltage, how does it affect your reliability, meaning errors? How does reducing voltage affect DRAM latency? In other words, can you get rid of some of the errors that you get because of reducing voltage by increasing latency? Because there is that relationship. Because as you reduce voltage, things become slower, right? Propagation delay becomes smaller. As a result, you need to wait longer to access data reliably. So there's a voltage latency relationship for reliable operation. And then based on some of the insights that we gather, assuming we gather some insights, can we actually reduce DRAM energy? That was the goal over here. So basically, it turns out you can actually adjust the supply voltage in DRAM modules, and that's what we did in this work. We modified the SoftMC FPGA platform to change the supply voltage to the modules. There's a voltage controller. You can read more about this. And basically, we tested a bunch of DRAM modules. These are actually low voltage DRAM modules to begin with. They're designed for low voltage. And you can read more in the paper. And you basically, how do you test for voltage? You iteratively read every bit in each chip under a wide range of supply voltage levels, 1.35 volts to 1.0 volts. So that's a 26% reduction in voltage. Now let's take a look at what happens to the fraction of cache lines with errors. And these are 3 different vendors. And by now, you know that there are 3 major DRAM vendors, right? You can guess who they are. So this is how they behave, basically, as you reduce voltage. Clearly, as you reduce voltage, at some point, you start getting errors. In this particular vendor's chips, you get errors early. So maybe they have a smaller voltage margin. In this particular DRAM vendor's chip, or both of them, you start getting errors over here. So they have a higher voltage margin, as you can see. And errors start increasing and becoming huge over here, as you can see. So this is 10 to the 2 is 100%, basically. You don't want to be over here. Clearly, you don't want to be even over here because 10 to the minus 6 is a very large number for error rate, actually. So this is expected, hopefully. So there's a minimum voltage without errors, and you can define that. Reducing voltage below Vmin causes an increasing number of errors, as you can see. And different chips operate at different points. And these error bars are actually different chips tested from different vendors. So this actually plots the distribution. Okay, so how do you actually understand this? How do you actually fix these errors? This is the relationship between supply voltage and reliable latency to operate without bit errors in that voltage, assuming circuit models. This is actually a simulation, circuit simulation that we did. It's also released. You can find it online. So if you reduce the voltage, you should really increase your latency to not get errors. And this is the curve. This is what the curve looks like. So it sounds nice. This is theory, if you will. Well, simulation, theory-based simulation. So basically, that tells us reliable low voltage operation requires higher latency. Now, the beauty is we have the infrastructure to test this theory. Right? You can actually plot exactly the same thing using real chips. Well, basically, you reduce the supply voltage and you try to increase the latency and figure out how many chips actually fail or not fail. Right? And this is what we're going to do. So this is what you see, basically. The curve looks very similar, essentially. This is the supply voltage, and we're reducing the supply voltage. I think this is one DRAM manufacturer. Maybe it's a combination. I don't remember. But you can see that I think it's one, not a combination. It's one of those that start getting errors at 1.10, as you can see. But basically, this shows the measured minimum activation latency to make sure the cells are operating correctly without errors. And this is a fraction of cells that are operating correctly. So clearly, as you go until 1.10, all of the cells are operating correctly at an activation latency of 10 nanoseconds. But once you jump to 1.10 volts, some cells require 12 nanoseconds or 12.5 nanoseconds to be exact to operate correctly. And that's 10% of the cells. But 90% of the cells still can operate at the lower voltage. Now, as you become more aggressive, you reduce the voltage a little bit more. The fraction of the cells that require higher latency increases, and some of them start operating correctly. Basically, there's no level There's no latency you can use to make sure that they operate correctly. They just don't operate correctly at that voltage level, basically. And as you keep reducing the voltage even more aggressively, you need higher latencies to operate some cells correctly, and fewer cells start operating correctly, as you can see, right? So if you add these rounded up, of course, for example, here, only 10% of the cells operate correctly at this level, and none of the cells operate correctly at the tested minimum latency levels. So this actually shows that, well, I already said this basically. Yeah, I mean, I think I already said a lot of this across slides, but basically this shows that DRAM requires longer latency to access data without errors at lower voltage, but some of the data you may not be able to access correctly. That's the idea over here. And the other thing that shows is the circuit level simulations actually verified with real DRAM chips over here. And you can actually calibrate. If you have an infrastructure like this, you can calibrate your circuit level simulations using the data that you get from the infrastructure. That's actually very, very valuable. Because otherwise you just do simulation and you don't close the loop, right? Here we can close the loop, meaning we can keep calibrating our circuit level simulations. So that's one observation. Clearly you can exploit this trade-off. You can reduce voltage somewhat aggressively. You can increase the latency so that you don't get errors. And there's also an ECC lever you can play, but we're not going to talk about that because this work doesn't do that. So there's also another interesting thing. There's some spatial locality of errors. You could also expect that, right? But it seems like some banks and some rows are worse off when you reduce the voltage. This is probability of a row with more than 1 bit error. You can see that some banks don't see errors, but some banks see a lot of errors. So some banks actually are less, let's say, tolerant to voltage reduction because of the way perhaps power delivery happens to those banks. We don't know exactly. This is a bit tough. But this exists. You can actually take advantage of it, right? You can reduce voltage selectively to different banks. You may not be able to do it in existing DRAM chips, unfortunately, because this requires different voltage supplies to different banks, which increases cost. But in research, you can do it clearly. And this work actually proposes a way of taking advantage of this. Basically, the proposal is, I'll go through this relatively quickly, but users specify some performance loss target. The goal is to optimize performance energy at the same time. Or optimize for energy, reduce energy as much as possible within a tolerable performance target, performance loss. Users specify some performance loss target, and there's a mechanism that selects the minimum DRAM voltage without violating that target. Then the question becomes, how do you predict the performance loss due to increased latency under low DRAM voltage? Because you're going to reduce the voltage, that's going to require increased latency, so you're going to get some performance loss. What is the prediction for that performance loss? So there's a model that this paper builds. You can take a look at it. It's interesting, but it's not the best model one can build. You can imagine neural networks also, by the way, here. You can actually, this is a linear regression model. In the end, it's some statistical model. Neural networks are also statistical models in the end, right? A better statistical model, let's say, assuming you can do the training nicely. So it basically has a model. The inputs are the characteristics of the application, like how many cache misses you have, how much parallelism you have, and the DRAM voltage that you want, potentially. And this gives you a predicted performance loss for different voltage levels, assuming that you need to increase latency somewhat at different voltage levels. And if your predicted performance loss is less than the target, you select the minimum voltage that satisfies that target, basically. And that's your final voltage. And hope that this works nicely. And if you actually do this in simulation, this shows that you get a lot higher energy savings than prior work. Prior work just changes the DRAM bus frequency and voltage, but I'm not going to talk about that. It's also our work, actually. A long time ago, we did this work with Intel and showed that you can actually reduce the voltage and frequency in real DRAM chips based on real data. But I'm not going to talk about that. That's also interesting. But this is more state of the art, if you will. So basically, you can get much higher energy reductions, especially for applications that have high memory intensity. Because that's where you actually gain benefits in terms of energy. Right? When you have high memory intensity, you're having a lot of activations in memory, and those are the ones that are costing a lot of energy. And prior work actually takes advantage of low utilization in the memory bus. You can reduce the voltage and frequency if the memory bus is not utilized. That's why the savings here at low memory intensity is higher, but it doesn't get much savings at high memory intensity because memory bus is almost always utilized. In that case, you're always accessing memory, which I believe is the case in many applications today. And the target performance loss, you can see that the target performance loss within the target. In this case, the target was 5%. But this clearly depends on the application, right? Maybe you're not able to tolerate 5%. In some applications, you may be able to tolerate 10%. Who knows? So this is slightly different work in the sense that it's not trying to reduce latency, but it's trying to optimize energy at the cost of latency, right? In the end, it's not very ideal in that sense. Ideally, you would like to reduce latency and energy at the same time. But this again tries to take advantage of the application tolerance to performance loss, not errors, to optimize, to get to a sweet spot between energy and latency. So you can see now things are getting complicated. We're relating multiple things, right? And using multiple levers. Okay, so let's talk about advantages. Clearly, we've discussed this. You can trade off between voltage and latency to improve energy or performance. This is not what the work does, but you could actually also think about improving performance by increasing your latencies, right? Certainly, it's possible to do that. No, what did I say? No, improving performance by increasing your voltages, right? Clearly, you could improve performance by increasing your voltages and reducing your latencies, but this comes at the cost of energy. So there's a relationship between these three things: energy, latency, and voltage, and performance. And you can exploit the high voltage margin present in DRAM, and we saw that that margin is relatively large. The disadvantage is now it requires finding the reliable operating voltage for each chip. So this is even higher testing cost now. And also the reliable operating latency at a different voltage level. So, and again, a more complicated memory controller. So these disadvantages will persist basically. Everything that we discussed requires more testing. You can do the testing online also, potentially. This online testing is harder, unfortunately, because you need to change the voltage, right? Changing the latencies are relatively easy in DRAM because you just change the timing parameter and test. Changing the voltage requires ramping up the voltage levels. And that takes time. So the overhead of this is a lot higher if you want to do it online. It's a bit unfortunate. I don't know. I mean, you can do it. So for example, dynamic voltage and frequency scaling in processors kind of does that. You do dynamic voltage and frequency scaling, but you also usually don't do online profiling. Some processors do online profiling actually today to shave off the voltage margins. So people have figured out that there is a huge voltage margin in processors also. Different operation conditions, you're actually wasting a lot of voltage. In some conditions, for example, you don't need that much voltage, so you can reduce the voltage. And some processors today, for example, a lot of IBM processors do it. They do voltage, dynamic voltage optimization so that they shave off the voltage that they use. Because this is very important for energy, actually. I believe some Intel processors do that, but Intel doesn't talk about this publicly. But IBM has written papers about it. In fact, a paper, there was a paper, if you're interested, there was a paper in Micro 2011 written by IBM that talks about this voltage optimization because they want to get rid of the additional energy of voltage and they figure out dynamically how to change the voltage of a CPU. In a sense, it's kind of similar. You just need to do it in the DRAM. But again, you complicate things. Okay, any thoughts? Yes, please.
Until now, like in the lecture, we have talked about many elements that could influence the performance, influence the...
Can you speak up a little bit more? Yeah. Maybe that's not working.
Influence the performance, influence the cost, and influence the energy. So I see like it's like a card game or what kind of game that it's like you press this button and you have this kind of output and you press that and they influence others. I think it's a little bit like we want to reach a kind of optimum that is specific for a certain task application or in different scenario optimal. And I was wondering if how small this memory controller could be. It can actually reach a kind of optimality that is it's called Pareto optimal.
Pareto optimal. Yeah.
So maybe, in your previous slides, you also mentioned linear regression. So maybe there's a kind of regression method that map each performance, cost, and energy to voltage, to error rate, to and the other one is refresh rate or whatever, and then in the end combine them together and then do this parallel optimization.
Okay, I see what you mean. So you basically want to build a model that takes some input and that configures the parameters, voltage, latency. Mhm. Mhm. I see, yeah. Mhm. Yeah, yeah. I mean, that requires a lot of smartness. Yes, I agree. I think it's good to imagine that. It's maybe there's some more research that needs to be done. But what we're doing, yes, exactly, is looking at some of these parameters in isolation, right? I think what you want to do is really optimize everything.
Yes, you know, this kind of linear regression we talk about is very easy, but maybe in real cases it's not linear, but in different.
Exactly, yeah, yeah. I think linear regression, yeah, exactly. I think there's a lot of non-linearity in the problem, so you really need something, yeah, more sophisticated, some more sophisticated statistical model. But I see what you're getting at. I think it'd be nice to have a controller that looks like this. I don't know how to build it, but there's a research problem there.
Yeah,
for sure.
Adaptive, like dynamically optimizing for the special application, what we need.
Yeah, I agree. I think that's a very good research goal. It's a bit more complicated. I think it's good to tackle parts of the goal. We're going to talk about, like when we talk about memory controllers, we're going to talk about reinforcement learning based controllers that optimize for performance, just one aspect. But I think what you have in mind kind of resembles that sort of approach, some sort of learning mechanism.
Yeah, but actually I target for all the different indexes.
Exactly,
together.
yeah. Mm-hmm. Yeah. So basically refresh, latency, performance, quality of service. Yeah, ideally, yes.
Because they're all related together, I think.
Yeah, I agree. It's tough to solve all of them at the same time, though. It's a very complicated space. Okay, that's good. You have some ambitious folks here that can do bigger research. Okay, so let me talk about something that's related, but that leads to something completely different, meaning using memories for security. So it turns out what we have talked about, this latency reliability trade-off, can actually enable you to generate true random numbers in DRAM and also evaluate physically unclonable functions. These are security primitives. It can also do other things in DRAM that enables you to quickly destroy in-memory data that I'm not going to talk about, but I may mention that. Let's talk about this one. So I'm not going to talk about physical unclonable functions, but it turns out as you reduce the latency, well, I'll give you the basic idea. As you reduce the latency of cells, some cells fail in a way that forms a signature of the device. So for a given latency reduction, you can have a pattern of cells in your DRAM chip that fail, and that's unique to your DRAM chip. So this is a signature of the DRAM chip, basically. Now you can identify the device, right? And this could be used as a physical unclonable function. It's essentially a physical unclonable function is a physical function that is used for identification or fingerprinting of a device. So this is actually fascinating. I think there are a lot of use cases of physical unclonable function of authentication, for example, attestation. I'm not going to talk about that. But this paper talks about that, and there's a lot more detail, and you can find it online as well as a talk. I will talk about something similar, except used for a different purpose. If you reduce the latency of a cell, some cells fail randomly. And can we take advantage of that? And that's the idea of random number generation in DRAM. Okay, I'm going to skip these. you can read that on your own if you're interested. But basically, when you reduce the timing parameters, it's again an experimental study, you get latency failures. A cell's latency failure probability is determined by random process variation. Some cells fail 50% of the time, some cells fail 80% of the time, some cells fail 90% of the time at a given latency point. Some cells fail randomly, 50%. So if you can identify which cells fail randomly at a given latency point, you keep testing that cell, and the failure pattern gives you a random number. Basically, if it fails, you encode as a 0. If it doesn't fail, you encode as a 1. And you keep doing that. That's a random number because this is based on physical random variation. That's the idea, basically. So let's take a look at why this happens. So this curve you've seen before, right? This is the bit line voltage, is time. When you do an activate, you do some charge sharing, sense amplifier becomes enabled, and the voltage gets amplified. And then you can do a read. And that's the activate latency, basically. There's some ready-to-access voltage level that I kind of ignored earlier, but I mentioned it. Now there's a guard band. This is the timing margin that we discussed. Now, process variation results in cells having unique behavior. Not all cells follow the same curve. Different cells are different curves. Some of them are strong, some of them are weak. Now, if you reduce the latency at which you're reading the cells, you can see that different cells have different probability of failure. This is also a probabilistic thing, basically. Not all cells follow the same curve every time, right? There's also noise that happens. So if a cell is really close to here at this latency, that's a good random number generator cell, basically, because it's probably failing randomly. But you can test these. So that's the key idea. Some cells have high chance to fail with reduced TRCD. Some cells have very low chance to fail. If it has 0% or 100% chance to fail, those are the cells that you can use for identification. But if it has 50% chance to fail, that sounds like a good random number generator. So these are RNG cells, essentially. And you can generate random values by repeatedly accessing these RNG cells and aggregating the data that you read. And it turns out there's a lot of tests you can do for randomness, and this passes all the randomness tests that are specified by National Institute of Standards and Technology. And essentially, you can generate random numbers at reasonably high throughput. And you can actually improve the throughput by doing it in parallel across many DRAM modules. Reasonably low latency and very low power, actually. So this is a nice DRAM random number generator. And this, you can read more in the paper. I just giving you the basic idea. There's a lot of analysis in the paper to show that this is random, the entropy is high, what happens at different temperatures, etc. Those are things for reading the paper, basically. Again, this is another paper that you can read if you want to get extra credit or just want to learn. Hopefully the letter one's more important than the extra credit, but there's another trade-off over there, right? Learning versus extra credit. Okay, does it sound interesting? I think this is fascinating, actually. This is something, I think this is something that's really novel. And I think similar effect can be observed at different memories. And you can also watch the lecture, which was delivered in an earlier incarnation of this course. But Jeremy graduated, so he's not going to deliver this lecture again. Well, maybe he's delivering it some other place. Let me give you another idea. This is not exploiting the latency reliable trade-off, but this is exploiting something else that was discovered. Ataberk, he's not here right now, but basically, it's quadruple low activation. I'm going to skip some of these slides. These are useful, I think, for you because, like, why would you want to generate random numbers in DRAM? Because not all computing systems have true random number generation hardware. By the way, this is true random number generation. It's not a pseudo-random number generator, right? Normally, you can have a pseudo-random number generator by using linear feedback shift registers and providing different seeds, but these are traceable. Meaning you can figure out the random numbers that you would get, assuming you know the seed, and you can discover the seed, etc. So true random number generation happens when you have a physical source of randomness that hopefully cannot be, let's say, hacked, if you will. It really generates true random numbers. Of course, if you talk about the theory of randomness, people, they always have some arguments about what's true random, what's not true random, but I'm not going to get into that. So I think basically DRAM-based true random number generators have another application. If you have processing in memory, for example, you also need random numbers over there, especially if you're doing security critical applications. So these slides are useful for that purpose. So I'm going to skip some of these slides. Basically, I give you the key idea. The key idea of quadruple row activation. So if you actually activate 4 rows with different data values, you can see the conflicting data values, then you can generate random values. So 2 rows have 1s and 2 rows have 0s. Now, what happens if you activate all those 4 rows? They compete with each other. And in the end, the result is determined based on the noise that's inherent to the process variation that you have in the sense amplifier and the bit line. So that's the basic idea. You activate 4 rows concurrently. How do you do that in real DRAM chips? It turns out this happens in real DRAM chips. And you violate the timing parameters between activate, precharge, and activate. And in some DRAM chips, you can open 4 rows, according to our hypothesis. And that leads to random values in the sense amplifiers. That's the idea. And this paper also does statistical testing, etc., and shows that these values are actually random values. So I'm not going to go through this again in detail because we don't have time, but you can read the paper. There needs to be some post-processing that needs to be done to actually correct. But that's true for a lot of true random number generators today. But you can read the paper. If you're interested in randomness, that's actually good. And maybe Ataberk can give a lecture about this. How many people would be interested in learning more about this sort of stuff? Okay, that's a lot of people. How many people would not be interested in learning about this? Don't be shy. It's out of my interest area. You don't count. You already saw, you already took this course. She's one of your TAs. And she already took this course and did well. That's why she's a TA, right? She's thinking right now, not well, maybe. Okay. It's good to have high standards and don't think that you didn't do well when you did well. Well, something is wrong in that sentence. Double negative. Okay, but basically, you can do this in real DRAM chips. And it turns out you get good throughput and low latency and better results than what D-range showed. And so there needs to be area cost, clearly. There needs to be some memory overhead because you need to dedicate some parts of your memory to do the random number generation. That's true for D-range also, which I've glossed over, but you'll see that in the papers. Now, temperature dependence is important because actually temperature affects the entropy that you get. So the cells that you think are basically this randomness, the rows that you think are going to produce random numbers change with temperature. So you need to have different rows for different temperatures, essentially. Okay. Okay, so this is a summary. You can read the summary also, but maybe we'll arrange a lecture that talks about this, since a lot of you expressed interest except for one TA. Okay, so there's a lot more over here which I'm not going to talk about. I think we're almost at the end of the lecture. Actually, reducing refresh latency is interesting. I'm not going to talk about that. Reducing memory latency by exploiting memory access patterns. Since we don't have time, I'm not going to talk about that, actually. But you can look at the slides if you're interested. There's partial restoration of cell charge, which is actually interesting. We talked about partial restoration earlier, but you can actually do more over here. We've talked about parallelizing refreshes and accesses. This is actually a latency optimization, in a sense. Instead of having refreshes and accesses conflict with each other in the same bank, just parallelize them in the different subarrays, for example. So this is an example of subarray level parallelism applied to refreshes and accesses being done in parallel. So that's another latency reduction mechanism, if you will. And as I mentioned, this is here is actually a real world demonstration of, partially real world demonstration of this work, which basically proposes something, and this work shows that you can actually do it partially in real off-the-shelf DRAM chips by violating the timing parameters. So violating the timing parameters actually gives you a lot of benefit. Okay, there's also a lot of other stuff like we're not going to talk about because we don't have time. Otherwise, we'd be here for all of the lectures talking about this stuff. I think we have a lot more other stuff to cover also. But power consumption is important. Similarly to what we've done, you can actually do real system power measurements. This requires some more infrastructure. So a lot of these studies actually require changing the FPGA-based infrastructure in some way, because power measurement was not something that we were doing, and that requires a lot of work. This actually required about 2.5 years to get it right. Initially, some undergraduate students burned a bunch of PCBs to actually get this working. But eventually it worked. So basically that's the summary. I think no, this is not the summary. Basically, there's a huge challenge in designing fundamentally low latency computing architectures. And I believe it can be done by tackling really the fundamental sources of latency, which is the way we're designing our memories and the way we're wasting latency. So this is actually, I would say that we're kind of wasting latency with this fixed latency mindset, one size fits all approach to latency, instead of exploiting the heterogeneity in the latency. Whereas here, if we design the DRAM memory microarchitecture differently, you can actually have lower latency. And these can be combined. There's no reason to think that they're not orthogonal. They're actually completely orthogonal. But I think, as we discussed earlier, this requires a change of mindset, right? And the mindset, as we discussed, was if your mindset is cost at the expense of everything else, well, you're not going to do this, clearly, right? But I think this cost-oriented mindset that's especially focused on the cost of a fraction of the system and not the entire system, like overall costs that we waste, for example, because of the high latencies, is misguided. So our current mindset, I think, is very misguided. It's really because of the way we design our systems, right? This you have this cost-based mindset in design of memory. That's true for all memories, actually, not just DRAM, but all memories in general. As a result, we're ignoring the bigger cost that we have in the entire system. It's like processing in memory, if you will, right? To be motivated that way, right? You're really optimizing for the processor, but it's really ignoring the great system cost, right? here again, we're ignoring the overall system cost that we get by not optimizing for latency, for example. And again, I think hopefully everything is clear that you need some intelligent controls to reduce this latency. Like all of these ideas require some sort of intelligence in the memory controller. So these are some common themes, I think, that you will see. Okay, I think I've discussed this. Now, ideas are applicable to other technologies. These are there are actually some more works that I could have added, but I didn't have time. But this is one example. In flash memory, you can also reduce latencies with somewhat similar ideas. Not exactly, but it's specific to the technology, but ideas could be similar. And I think in other technologies, for example, in non-volatile memory technologies, I've seen a lot of papers that use ideas of subarray level parallelism, for example, to reduce latencies. There are a lot of interesting papers over there and similar ideas as what we've discussed. So don't think that these ideas are just for DRAM, basically. Some of them are exactly applicable to other technologies. Some of them are, with some thinking, can be adapted to other technologies. So they're actually quite general ideas. So keep that in mind. So that brings me to the end. And I think we've also exhausted the time. We've eaten away from some of the margin also, actually. But not too much. Okay, so we have not started. As I expected, we have not started memory controllers, but we will do that next week. Tomorrow, we're going to talk about something that will be in your next lab, which is talking about real processing in memory systems. So we're going to introduce a new lab this semester. So you're going to be lucky in testing that lab. You're going to be programming real processing in memory systems. I think it's important. I want to keep this course at the cutting edge. I don't believe that such a lab exists anywhere in the world. So hopefully that'll be interesting, but there may be bugs in the bag also. So bugs in the lab initially also. So you're going to be guinea pigs in a sense, but that's what means to be in the cutting edge, unfortunately. Whenever you're in the cutting edge, leading edge, you always are subject to some errors. So you'll see that in the running of the course. But Juan is going to talk about the UpMem system that will be useful for you to do the lab. So hopefully you'll attend. Okay, take care. I'll see you tomorrow.